To the best session in PLDI. This session is accelerator compilation. We all love that stuff. We've got some excellent talks here. Please come in, make yourself comfortable, stay for the full session. I've read all these papers, they're fantastic. And to get us started, I couldn't think of anyone better. Abhinav Jangada is going to tell us about fast matrix multiplication. Abhinav is my colleague at Microsoft. I get to learn from him every day, and now you have the awesome opportunity to learn from him now. So take it away, Abhinav.
Thank you, Tyler. Thank you everyone for coming. So today I'm going to talk about subcubic matrix multiplication on GPUs. Just to start, so we know matrix multiplication is very common, and to set the notation which we'll be using in this talk, a matmul takes two matrices A and B, and A is of size m cross k, B is of size k cross n, and the output C is of size m cross n. So we are going to represent this matmul with m and k, these three sizes. And it's a very common operation. We see it is being used in scientific computing, where we have large float bit weights, and also in machine learning, where we care about smaller low precision types. And so how do we compute this matmul? Well, it's usually done using this 3-loop cubic algorithm that we are all familiar with, m and k. And over the last several decades, highly efficient parallel implementations of this cubic algorithm have been developed for CPUs, for GPUs, and these are very efficient that they obtain close to peak flops. So the question becomes, if they are very efficient, can we even make matmul even faster than that? And that is what I'm going to talk about, that our system subcuber, it can make matmul faster up to 23% than NVIDIA libraries. And as you can guess, it uses subcubic algorithms. So a very common example of subcubic algorithm is the Strassen algorithm, which we have always, I'm so sure everyone has learned about that. And it runs in n to the power log 7 base 2, which is n to the power 2.8 complexity. So how it works is it's a recursive algorithm. So at every recursion step, it's going to divide these matrices C, A, and B into 4 parts: C0 to C3, A0 to A3, and B0 to B3. So if we apply this recursion step once, we are going to get, instead of 8, we are going to do 7 smaller multiplications. And theoretically, since we are doing 7, not 8, so we can get 12.5% speed up over the cubic algorithm. Let's do it again. So in that case, we'll have 49 of these smaller matrix multiplications. That would mean 23.5% speed up. Now the question is, how do we actually execute this on a GPU? Now there are several Strassen algorithms, and one of those algorithms is the Strassen-Vinograd algorithm, which has some input summations that you see on the left-hand side, and then it does 7 smaller matrix multiplications, and then it does some output summations. So let's look into this particular M4 that takes this I1 and I5 as input. So I1 is A2 minus A3, I5 is B1 minus B0, and the output of M4 is used to update C3 and O3. And there are several Strassen family of algorithms. The original Strassen algorithm, which was probably the first subcubic algorithm, had these 22 input and output sums. Then the Strassen-Vinograd has 15. Alternative basis Strassen, which is the latest one, has 12. And as you can see, since with the decrease in input and output sums, the maximum absolute error as compared to the cubic algorithm also increases. So which Strassen algorithm is best? It depends on your application. If you want, you can trade runtime and numerical stability based on the application. So how do we execute these Strassen algorithms? Well, a very common baseline, a very old baseline, was to execute 9 different kernels. So the first kernel, CUDA kernel, is going to compute those input sums. The next 7, it's going to compute the 7 matrix multiplication, and the last kernel is going to compute some output sums. But this approach is always slower than NVIDIA's libraries for float 16 and very large sizes, up to 16,000. And the reason is simple, that the first and the second kernel, the last kernel, they can take up to 50% of the total time, because what they are just doing is reading a memory, computing something, and writing it back. So the problem is not actually the summations here. The problem is the memory excesses, and how can we avoid that? And the situation becomes even difficult at L is equal to 2 because then they are going to have 51 of those smaller kernels. So how can we optimize those manually? And that is why I think a compiler approach was the right call here. So Subcuber is a compiler that takes a Strassen-like algorithm written in PyTorch API. It will extract that graph of the PyTorch. It takes data type, the matmul sizes, and the GPU spec, and outputs a efficient CUDA code. And it has several passes, like it generates an IR, it generates a kernel schedule, does a lot of fusion to generate that code. And that is why it performs significantly faster as compared to NVIDIA's supplied Cutlass and Kubeless libraries. For example, float 32 is up to 23% faster, float 16 is up to 16% faster, and the sizes in this LLM that we see, like Llama, Phi, and Qwen, those are also up to 16% faster. So let's look into detail how Subcuber works. And the first pass of the Subcuber is to create that IR. So it will go through the Strassen algorithm and create 4 AST nodes. So the first is, well, input sum. We are going to compute an input sum node. The other is a matmul node that represent each submatmul. The next is a combined input sum and matmul node. And the last is a Strassen node. So that represents all of this Strassen algorithm. Now each of these nodes map to a different Subcuber kernels. One is, which can compute an input sum, which is K1 kernel. The other is we can compute a submatmul through the K2 kernel. And the last is a K3 kernel that computes both input sum and the submatmul. And then there is a K4 kernel that computes the Strassen on each algorithm on each tile. So I'm going to talk about K3 and K4 because they are the most interesting. And all of these kernels follow the same tiling methodology that we all know of. We divide that output C into different tiles of the same size on 2D blocks. And to compute a tile, we only need to load that portion of A row and that portion of B column, nothing else. So each tile can be executed independently of the others. But the point here is each tile is also computed serially. So there is a long loop of K in a dimension that has to be done. And that is how the K3 kernel actually works. So the K3 kernel, it is not only going to compute a submatmul, but it is also going to compute input sum for all other submatmuls so that the other submatmuls don't have to do anything. And if you look in the Strassen Winograd algorithm, we see this particular M0. M0 is just A0 multiplied by B0. It doesn't require any input sum. So on the figure that you see in the down, so M0 is being computed with A0 and B0, and each iteration of the K loop, it's going to the kernel is going to load a tile of B0 to B3, a tile of A0 to A3, and then also going to write a tile of I1 input sums. So by interleaving these memory accesses with the computation, we can actually overlap these memory accesses for input sum with the computation, and that reduces the input sum time by 2 to 5 times over the separate sum kernel, and achieves almost the same you would expect the memory bandwidth of the GPU. The next kernel is the K4 kernel, and it works on each tile. So let's zoom into one tile, and it divides this tile into 4 parts. It divides the A into 4 parts, divides the B vector into 4 parts, and then run a Strassen algorithm on each to compute that tile. Now all of these I1 to I8, they have to be stored into the cache, so because they are being used through M0 to M6. But it also only loads A and B from the cache. So there is no more memory accesses here. We just don't have any other memory accesses. So if we look on these 2 kernels, we can think of these as kernel schedules. So for level is equal to 1, for the first recursion level, we have 2 schedules. One is, we do the K3 kernel, which is compute both input sum and submatmul, and the others are K2 kernel. And the good part about this schedule is it can give good performance on large matmul sizes. But because these are 7 smaller kernels, it is bad for small sizes, because on small sizes we want single kernel. And that is where the K4 schedule works fine, where is a single kernel, it gives good performance for small matmul sizes, but it's bad for large matmul sizes as it has high cache usage. Now we can think of these schedules as actually transformations, and if we recursively apply these transformations, we can get higher level schedules. So as an example, consider L is equal to, consider that we want to get schedule for 2 levels. We want to apply Stressen algorithm twice. So first we apply the transformation 1, which is we convert a matmul node into 6 smaller matmul nodes. Then we can convert these 6 smaller matmul nodes into some other transformation. So let's say M1 to M3 are being done by this transformation that uses Stressen MM node, while all others can be done with this other transformation, which we have already seen. So since there are just 2 transformations and there are 6 cases, with each level the schedules are just exponential. For L is equal to 1, we have 2 schedules. L is equal to 2, we have 64. L is equal to 3, we have so many. I didn't even calculate that. So subcuber has this greedy algorithm which we can look into the paper and with a cost function, and that is how it finds the best performing schedule. Now these kernels are basically based on NVIDIA Cutlass, which is a library by NVIDIA that has a highly efficient cubic implementation. And these kernels right now supports Ampere and Hopper architecture. So they have CUDA cores, tensor cores, different floating point types, different ways to transfer from global to shared memory, etc. Now let's look at some evaluation. And here I'm just going to talk about H200 results. There is also results for A100. Those are in the paper. And the baseline here is definitely NVIDIA Cutlass, which we want to beat. And the other is this previous work of fused InSum that fuses input sum loads in each submatmul. And that is always faster than the separate sum kernels. So I'm not going to present results for that. And there are more baseline paper like QBLAS and QBLAS LT. So first, let's look at some square matrices for floating point 32. And on the right hand side, the graph has the x-axis. So the x-axis is the size of the matrix, and the y-axis is the performance improvement over Cutlass. And the orange lines are the one that represent subcuber for first level and the second level, and the fused InSum are the blue lines for first and the second level. And as you can see, that the subcuber reaches theoretical speedup of 23% at size 3584 and more for 2 level, and also the similarly 11%, 12% for first level. While the blue lines, which are for fused InSum, they never reaches the theoretical speedup. So they are only 16% for the second level, for example. More interestingly, the subcuber is faster for 512 and higher size, which is 3 times lower than what it was for fused InSum. So ideally, we want to push this graph as to the left as much possible, so that it is faster for as small size as possible. So right now, it's possible to do with 512. And we also have this float 16 results that uses tensor cores. The problem with tensor cores is the tensor cores are 16 times faster as compared to the CUDA cores. So the memory to compute ratio changes drastically. And that is why the size where subcuber is faster is 4096. And although for first level it reaches around 11%, or 12%, but for the second level it is only 16% faster. So there is still a gap to do. Then we also picked some matmul sizes from different LLMs and tried subcuber on those matmul sizes. So we have Llama 3, 5, 4, and QN3, and these represents these 3 LLMs represents different small LLM, medium LLM, and a very large LLM. So I'm going to just show this improvements for Llama, and we can refer 5, 4, and QN3 in the paper. And so Llama has 2 matrix multiplication, MM1 and MM2, and on the graph on the right, the bigger graph on the right shows the speed up over Cutlass for batch size 1 to 32. And as you can see, the MM1 reaches 16% for the biggest batch size that Llama 3 can support, and that is because MM1 is very big, and we can apply 2 levels, while MM2 reaches 12%. And this leads to a faster end-to-end inference of 4 to 8%. Now, it's not just, so I only presented for Strassen Vinograd, but we also have similar performance for all other Strassen algorithms. While the existing works, they were only focusing on optimizing a particular algorithm, for example, Strassen Vinograd or the Strassen algorithm, and they were designed when the tensor cores were not even present. While the subQBER supports all of these and provides very good performance. So in summary, I think it's possible to have subcubic matmul on GPUs, and I'm happy to take any questions. Thank you.
All right, let's see, Ganesh has a question.
Yeah, very nice talk, Abhinav. Yeah. So long ago, when I heard Strassen, I asked my numerical friends why is it not being used, and they said it's the error.
Yeah.
So I looked at your paper, and you have L2 norm error.
Yeah.
But there's also a problem of backward instability. So
Yeah.
in your experience, is this mainly meant for machine learning or for HPC? Because the acceptance of these algorithms will depend on what they're looking for in terms of error.
Yeah.
I want to understand. I'm not an expert, but I want to see your opinion. Yeah.
Yeah, so for first in machine learning, we have seen several works that actually have way higher error rate as compared to the Strassen algorithm. So it should work. But in my experience, if we just train with this algorithm, with this implementation, and do inference, it should be fine. But the problem is, training with one algorithm and then doing inference on the other algorithm. For respect to the scientific computing, I'm not so sure about that. I'm not much aware of it. But the recent papers show that for float 16, for float 64, the error rate is anywhere between 10 to the power minus 9 to 10 to the power minus 7. So I don't know, it might be okay, yeah. Yeah.
Great talk. Did you compare this algorithm with stream K or split K kind of matrix multiplication?
So those NVIDIA Cutlass results are the best that they could possibly do. Yep.
And another question I have is the end-to-end inference. So the performance is not as compared to the GEM performance. So is it because of the launch latency, because you're launching these tiny kernels, and that takes basically start dominating when you have these small gems?
I didn't understand the question, actually.
That's okay. We'll take it off.
Okay, that's fine, yeah.
Ahmed, do you want to start setting up real quick while we take the last question?
Yeah, very cool talk. Thank you so much. I wanted to know, I like the results you had with FP16, and you pointed out that that requires a larger K before there's an advantage, because basically the base speed up is smaller. If we go even lower precision, right, FP8,
We're going to be talking about parameterized algorithms and complexity for function merging with branch reordering. Ahmed Zahar is going to be giving the talk from Hong Kong UST. And so this is going to be really interesting. I'll let you take it away.
Thanks. Hi, everyone. I'm Ahmed Zahir, and today I'll be presenting our work about function merging. This is joint work with Amir Gouarshadi, Karim Kychukov, and Tian Xu. So let's start. Okay. Compiler optimizations, they usually aim for speed. They want to make the compiled code run faster. However, there's another class of compiler optimizations which aims to reduce size. And why would you care about reducing size? Well, there are applications where you do care. For instance, in mobile applications, you want to keep your download size small. And in embedded systems, you have very little resources, and program size can be a serious overhead. So we look at a particular code size optimization called function merging. There, you're given as input two functions, f1 and f2. And what we want to do is that we want to construct a merged function, f star, such that it captures the semantics of the two functions, and we want its size to be as small as possible because we're optimizing for size. So I'll give a running example now, and I'll make a simplifying assumption that size is measured by the number of lines. So here are two functions, f1 and f2. They both take a parameter x. And here's one way to merge them. We have this merged function, f star. It also takes a parameter x, but it also takes this selector parameter b, which is when set to 1, this function will simulate f1, and when it's set to 2, it will simulate f2. I'll go back to how this function is constructed, but the point is that now we can completely remove the body of f1 and replace it with a single call to f star, and similarly for f2. And in this example, we actually managed to reduce code size before and after. It was 23 lines, now it's 22. So in this example, function merging was successful in reducing size. Okay, how do we do the merging? The state-of-the-art approach for this is based on sequence alignment. I will overview this approach for you because we build on top of it. Basically, you view the two functions as strings of instructions, and then you align some pairs of instructions across the two functions. And after that, for the aligned pairs, you just merge them into one and maintain one copy in your function. And for other instructions that say appear only in f1 but not in f2, then you put them under a condition so that they are only executed when you're simulating f1. And of course, the more aligned instructions we have, the more merging we do, and the smaller the merged function is. So let's see this in our example. Here are f1 and f2, and here is an alignment. We have these green boxes which map identical instructions in the two functions, and we also have things that only appear in f1 but not f2 here in red, and similarly for f2 in blue. And what's important about these arrows is that they should not cross. And the way we construct the merged function is we basically do a simultaneous scan of the two functions from top to bottom. Whenever we see a green instruction, we just put it. If we see, say, a red instruction, then we put it under the condition that b is equal to 1. So here it is, green instructions put as they are. This one was red in f1, now it's put under this if condition. So it's only executed when we're simulating f1. Okay, so we want to align more instructions, and this idea gives rise to this problem, sequence alignment. You have two strings, and you want to compute the optimal sequence alignment between them. And then the bulk of this approach is to basically reduce function merging between two functions to sequence alignment over them, but viewing them as strings. And how fast can we apply this? Well, sequence alignment is an undergrad classical problem. The textbook dynamic programming solution, you can apply it here, and you'll have an algorithm with this running time, the size of the first function times the size of the second. Okay, so this is a great approach, very successful, but it has a drawback in that it sees every function as a single fixed string. Whereas in reality, you can obtain different equivalent strings for the same function by reordering some of the branches. So define this set, reorder of f, to be the set of all strings that we can get by reordering branches in f. And now we consider this more expressive formulation where we want to first try all, we want to first try all possible reorderings on F1 and on F2, and then for each choice, we do the sequence alignment and we take the best choice. And the hope is that this does better than vanilla sequence alignment on a fixed string. Okay, so let's apply this here. If we look at F1, we have this FLF with 2 branches. We can swap them to get this function, which is equivalent but syntactically different. And by doing this, we can actually get a better alignment. And we construct the merged function as before, and now we have even more size reduction. So from 23 to 22 with the basic sequence alignment approach. By adding branch reordering, we cut 2 extra lines. Okay, so all of this is just to tell you that this is a problem that we're solving. And in this paper, we look at this problem from point of view of algorithms and complexity. And our first result is a negative result, basically saying that this problem is NP-hard. So before, without branch reordering, it's polynomial time solvable. We add branch reordering, now it's NP-hard. So what can we do about it? We can use this paradigm called parameterized algorithms, where instead of trying to solve the problem in the general case, where it's known to be hard, we solve it on a restricted subset of the input space. In particular, we apply this framework. We identify some parameters or features of the input such that these 2 conditions hold. First, we want it to be that for inputs that we care about in practice, we want these parameters to be restricted. And we also hope that restricting such parameters would allow us to design fast algorithms, which would overcome the hardness for the general case. If we do both of these things, then we're happy. We have a fast algorithm, and we manage to work around NP hardness. And the rest of our paper is just an instantiation of this framework. So what are the parameters or features we look at? We look at branching factor and nesting depth. Branching factor is the maximum number of branches you have at any branching point. Nesting depth is how deep you nest your branching constructs. For example, in this function f1, we have this FLF, which makes a branching factor equal to 2 because it has 2 cases. If we had an f with 5 cases, then the branching factor would be 5. For nesting depth, here we have this print, which is enclosed within a for, within an if, making the nesting depth 2. Okay, and our hypothesis is that these parameters are small. Their values are small. You'd expect that they are considerably smaller than the input size. So our 2 algorithms, they rely on this hypothesis. Okay, so we actually have 4 parameters for each of the 2 functions. We have branching factor of f1 and f2. Let's call them b1 and b2. And the nesting depth of f1 and f2. Let's call them d1 and d2. And our first algorithm is concerned with the case where we restrict all 4 parameters. So we give an algorithm with this running time. It's polynomial in the input size and exponential in the 4 parameters. So in general, this is not a fast algorithm. It's very inefficient. But if you restrict the 4 parameters, meaning that they have small values, then this term actually becomes acceptable. And this is polynomial, so the overall running time is efficient. And then we give a second algorithm, which gets rid of the dependence on one of the depth parameters. So instead of requiring that all of them are restricted, we only require 3 of them. So we give an algorithm with this running time, polynomial in the input size, well, worse polynomial than before. But this exponential dependence only has b1, d1, and b2, so it does not have the depth of the second function. So it can be arbitrary. This is basically a highlight of our results. And in the remainder of this talk, I'll just give some intuition behind the main ideas of these algorithms. So what about other restrictions? Well, for our NP hardness result, we show it for very simple case. So this already tells us that a lot of the other restrictions are already hard. But there is one open restriction where b1 and b2 are restricted, but the depth of the 2 functions is unbounded. Okay, let's get into some technical details. Here's our problem again. And the bottleneck here is this set of reorderings, which has size exponential. And we actually don't care about this set itself. We care about sequence alignment. So our starting point is the intuition that if you take the textbook algorithm for sequence alignment, it has this very nice property in that it's kind of an incremental and simultaneous scan of the two strings. So there you would have a state for that has 2 pointers, I and j, that go through the two strings, and then they just keep moving to the right in one direction. So we use this insight in our algorithm in the sense that we do an incremental and simultaneous exploration of the set of all reorderings of the first function and the second function. And as we're doing so, we compute the sequence alignment, the best sequence alignment on the fly. So let's give some details on how to actualize this intuition. First, we do some abstractions. We represent programs as graphs. This is basically reading the code from left to right instead from top to bottom. So we have these white nodes which carry instructions. And we have two dedicated left and right nodes corresponding to the first and the last line of the function. And for branching points, we model them with these solid nodes. So for example, we have this f_elif. It's modeled by this node here, and its two branches are modeled by these two regions below it. Okay, so remember the bottleneck was the set of reorderings. Let's try to understand this set of reorderings by traversing this graph. So we can design an exponential time algorithm, a recursive one, which does this. So it has 3 parameters: a currently visited node u, set of all visited nodes so far, and a string of all instructions we accumulated up to this point. The interesting case here is that if we're traversing a node carrying an instruction, then there's no branching. Then we just move to the next one. We append the instruction to S and move on. Otherwise, we have a branching. So we look at all the branches that are not visited yet, and we explore all of them. So this algorithm on its own is very useful, but it reveals a very crucial insight in that the number of pairs, nodes we visit, and set of visited nodes, its size is actually polynomial in the input size and exponential in the parameters. So this is a crucial lemma of our algorithm. I'm not going to prove it, but we use it, and we also extend this algorithm to scan 2 functions instead of 1, and also compute the sequence alignment as it computes. And now we have a dynamic programming algorithm with this many states and this much work per state. We give further optimizations to optimize the work we do at every state, and we have our theorem. I will say a few words about the second algorithm, which I think is quite interesting. So the idea behind it is that we view the first algorithm as a weighted reachability on a finite graph. And then we observe that if we take the set of visited nodes, say, of the second function, the set x2, its behavior as this algorithm proceeds mimics a stack. And the height of this stack is corresponds to the depth of the node that we're at. And this insight allows us to reduce the problem to reachability on a weighted pushdown system. And then we use classical reachability algorithm to get this running time. This is it. Thank you very much. I'll be happy to take questions.
Great. Who has questions? Let's see. We'll go Krish and then you.
Thank you. Excellent talk. Have you considered the possibility of removing branches and then performing the alignment of functions?
Removing branches?
Yes. You can eliminate some branches and then considering the possibility of aligning the functions. Or another example would be you're talking about the branch factor. So you can take your function and you can make all the branches as one-sided branches. So the branching factor becomes 1, and then try to perform the alignment. Can you comment on this, please?
Oh, you mean taking, say, 3 branches and then reduce into an F, and then in the else you put the 2 branches?
Yeah.
This is an interesting question. the reviewers were curious also about it. So there, what will happen is that you will blow up the depth. So you see our problem depends on both the depth and the branching factor. And also by doing this, you lose some of the expressivity because some of the permutations of the 3 branches will not be achievable by doing this, this transformation. So it's kind of a balance, like using this transformation, you can do a balance to where you reach both small branching factor and nesting depth.
One more question. Are you doing this at the source level or some intermediate representation level?
Well, we don't have experience yet, but we expect that if this is implemented, it would be at something like LLVMIR.
Thank you very much.
Thank you very much.
Hi, thanks for the talk. So you focus on branch reordering here. Have you considered reordering statements that don't have dependencies, or does that have kind of similar problems of exponential blowup and so on?
This is an interesting question. It will kind of add an extra degree of freedom to the problem, and it will make it much harder. We haven't looked into, like, we don't know the exact complexity if you allow both branch reordering and reorderings of independent instructions. But yeah, this is something we might look at for future work.
Yeah, that makes sense. Thanks.
I see. Yep.
Thank you, great talk. I'm wondering if you can view this problem as a special instance of anti-unification modular equality. And my second question is, like in reality, like there are all these different equalities beyond branch reordering. So have you considered, for example, doing some parameterized algorithm over, say, an E-graph?
What's this problem? Something modulo, something? I didn't.
Anti-unification modular equality, or E anti-unification.
Oh, I'm not familiar with this problem, so.
Could you comment on if it's possible to have some parameterized algorithm over an E-graphs, which is a graph of equivalences between programs?
I don't know how E-graphs would also have this branching factor. I'm not very familiar with E-graphs, but yeah, we can discuss it offline.
Thank you.
Great. While we take another question, Yifan, can you start getting set up? Now that we're all have our blood pressure up just a little bit, we're ready for the next talk. This talk's going to be about operator fusion. Those of us who program GPUs love fusion, and this is a way how to do a really good job of it. So Yifan from UIUC, take it away.
Yes, thank you for the introduction. So that was a little bit of interruption, right? So from the fire alarm, let's use some power from the sea to stop that. I introduced you Neptune. I'm Yifan from Illinois. This is my work, and I will tell you a story of how breaking the program and fixing it can bring us better operator fusion and better compilers. So Neptune is a deep learning compiler. The task of a DL compiler is to take a DNN and compile it to the hardware with good runtime performance. DNN here can be CNNs, LSTMs, large language models. Many large language models today are built on the attention mechanism, which turns out to be an interesting case for deep learning compilers. So let's pay some attention to attention. Mathematically, attention is simple. 2 matmos, a softmax, some element-wise operation. You can describe what attention does in like 5 lines of code. Implementation-wise, that got ugly. Kernel engineers write this instead, goes on for a few screens to get serious performance. So the gap between the math and the kernel you have to write today indicates that something is missing. Attention escapes compilers today. Compilers today cannot start from the simple math and produce a kernel with the performance that matches your manually implemented ones. So in the case of attention, we can actually pinpoint a main reason for that. The compilers cannot figure out an important type of optimization, and that is flash attention. Flash attention provides an alternative computation order for attention. So instead of fully calculating matmul 1, then softmax, matmul 2, flash attention does 1 tile of matmul 1, 1 tile softmax, 1 tile matmul 2, and move on to the next tile for the entire program, and so on. That means smaller tiles of data fitting on the faster but smaller caches of devices like GPU SRAM, the memory overhead decreases, and flash attention runs faster. Well, that rang a bell, didn't it? That is operator fusion, both in terms of the benefit and the pattern. And operator fusion is a classic optimization. Many existing compilers can already do that, except they all fail on attention because there is more data dependency in attention. To be specific, that means reductions in the softmax and matmul that is beyond what classic operator fusion algorithms can do. Neptune fixes that problem. In Neptune, we invent a more powerful, novel type of fusion. We simply call that advanced operator fusion, and closes the gap between the math and the kernel. And Neptune advanced fusion does not just work for attention. It generalizes to a class of different programs. In this process, we find out that there are many programs waiting to be fused in this way that today's compilers cannot. And in Neptune, we finally have the right tool to do this natively, automatically, within a compiler. So advanced fusion, that is the first main contribution of Neptune. The way advanced fusion works, as I promised, this is a story of breaking then fixing the program. We implement that idea in 2 variations. Both compiler passes are general over different programs. If you apply them back to our attention example, you get familiar results. Applying rolling update to attention gives you flash attention. Applying the other variant, what we call split K update, gives you a structure like flash decoding. And there's more. Neptune has a special design where the optimization pipeline is 2-staged. There is a loop IR, which is the higher level IR for high-level optimizations, just like our advanced fusion. And there is a tile IR on the bottom that is for the more hardware-specific optimizations. This is perhaps easier to see in a full system view of Neptune. Advanced fusion work on loop programs. It is in the loop optimizer as well as many other loop transformations. Then in the second stage, Neptune actually uses existing tile compilers like Triton to perform highly hardware-specific optimizations. Neptune's own tile IR, we have one, easily maps to the input language of the tile optimizers, and these 2 stages are connected by a translator that converts loop to tile via tensorization. There are 2 inputs to the entire system of Neptune: the definition of the operator and a small high-level schedule template that is for the loop optimizer. The schedule template can invoke transformations available in the optimizer, such as our rolling update fusion. This idea is similar to the algorithm schedule split in existing schedule-based compilers like TVM, if you are familiar with that, except Neptune's schedule is much more concise because a lot of optimization steps would be downstream and automated in the tile optimizer. Here is an example program in Neptune's loop IR. This program has 2 loop nests. The first one is a reduction. It runs over a 2-dimensional input and gives you the per row max, which is the vector here. And the second loop nest is an element-wise operation between the input and xmax to give you a 2D result of xexp. Now, this example also shows, well, it's a simplified case, but it shows how why flash attention style fusion is difficult. We are essentially asking to fuse the second loop nest under the reduction loop of the first nest. Here, that will be the J loop. If you force the classic operator fusion to do that, you get a program that is incorrect. And to see why it is incorrect, check this out. That's the input. That's the data dependency diagram of the original program where we calculate xmax first before moving on to xexp. And in the incorrectly fused program, the data dependency is changed. So because everything is under the J loop, we are calculating xmax and xexp simultaneously. We are essentially reading from xmax too early before it finishes. Compiler textbooks say this is a violation of temporal data dependency. Today's tensor compilers say this fusion is illegal and will reject it. In Neptune, we say we do the wrong fusion anyways. Break the program, then we change the computation in the program to fix the result, which is now something classic fusion cannot do. Let's use a slightly longer example. Our previous one adding a row-wise sum at the end, so we have 2 reductions. This is, by the way, similar to softmax. Neptune sees this program. It first applies the wrong fusion, which gives us this program on the right-hand side. Next, we find the fix for the program. We don't apply it on the first reduction. We don't apply it on the element-wise operation. The fix happens to the second reduction, where instead of taking a normal sum, you are multiplying the current sum with this term here to fix the result. That is what we call the repair term. And the key insight of Neptune fusion is finding the right repair term and adding that at the right place gives us a program that is correct again. So how do we find this repair term? Neptune has an algorithm for automatically doing this for general programs, and we have proof for its correctness. The margin here is unfortunately too small for the proof. In our paper, we have like 5 pages of proof and derivation to show how to do this and why it's correct. Here, instead of saying the proof, I'm going to give you an intuition of why Neptune fusion generalizes. So let's look back to our fused example program. This program says a few things about the computation in one place. There is the loop structure. And within the loop, there are a bunch of scalar expressions doing the computation with some data dependency. Now the loop structure is already good thanks to our naive fusion. So we want to turn to the next thing, that is the data dependency described here, which says we have a pair of reduction and an element-wise operation in between, and both the first reduction and the element-wise read from the input array. Well, by the way, Neptune can easily deal with more complex data flow, and that is treated in the paper. Back to our example with the loops dropped. Now the next thing we want to figure out is what kind of computation is being done, and we want to describe it in a way that is independent from the data dependence. And that means we want to extract the scalar expressions we are using for the computation. For the first reduction, it's simple. It's the max operator. And perhaps surprisingly, Neptune doesn't really care much about what's being done in the first reduction, the computation. But we do care that in the element-wise operation, we are reading from the first reduction as well as non-reduction inputs. So we want to label them separately. We can call them R and C, and that gives us an expression G of R and C, which is exp C minus R. And we can do the same thing to the second reduction. Because it's a summation, we can get just X plus Y. The reason why this is important is now it allows the Neptune repair term algorithm to only look at scalar expressions. So F and G are expressions as inputs to the algorithm, and it gives you a repair term also as a scalar expression automatically. This is essentially a symbolic solver, and it's built on SymPy in Python. And this is why Neptune Fusion can automatically apply to many different programs. We have applied it to not just softmax, attention, but also L2 norm, RMS norm, and performer. And in many cases, we observe significant performance gain. For example, here in L2 norm, we are getting like up to 6 times performance benefit just from the fusion. We will see more of that in the evaluation. Now, briefly on the other variants, which is the split K update. So in rolling update, everything is under the same loop nest, and the repair term is here. In split K update, the loop structure is different. We want to create 2 loop nests. The goal is this. We want the first loop nest to be fully parallelizable. It runs local reductions. And then the second loop nest is where we change the computation to fix the result. So this gives us a different trade-off point compared to rolling update. You get more parallelism at the cost of a little bit of data stored in addition. Back to the full pipeline, a few words on this because there's an interesting design decision I wanted to show you. But before that, let's see how loop and tile programs can work together in the same pipeline. Just to make things even simpler, this is a matmod in Neptune's language. So when the program comes in, first it runs into the loop optimizer, which does multiple things like tiling and parallelization, which gives you a program like this on the bottom, which is optimized by the loop optimizer. And then next, what happens is the loop to tile translator will latch onto the inner loops of this loop structure, as well as the compute statement, and translate entire of that into one tile statement. So now we are in tile IR category. And then you can see there is a clear separation of obligation between the loop and tile optimizer. The loop optimizer created the outer loop structure, and now it is time for the tile optimizers to take on the dot product and optimize it. And it turns out tile languages are quite good at that, at optimizing these tile dot products, for example. So tile languages like Triton, TileLang, there are many more of them. They are good at automating some low-level optimizations, like if you write a dot product, it will automatically figure out how to use tensor core product for you. But that doesn't mean writing kernels in tile languages is easy. You will still need to figure out all of these low-level optimizations, as well as high-level optimizations like the advanced flash attention style fusion we just saw. And then you put all of that knowledge into the tile code you end up writing. So the position we take in Neptune is we want programmers to start from mathematical expressions, not write tile language, tile kernels, but then we want the compiler to be able to bring the mathematical expression all the way down to CUDA heap level of performance on the hardware. And that is asking a lot of the compiler, so we want to get all the helps we can get, including reusing existing tile compilers for our pipeline. That is why we made this design decision. Now let's see how effective Neptune is with its design. We have evaluated Neptune on 10 different variants of attention, 6 prefill, 4 in decode, as well as non-attention operators like these 3 I mentioned earlier. And for each of them, I vary the input shape, such as the sequence length of the input. And for each of these setups, I also evaluate them on different GPUs, including 1 AMD GPU and 3 NVIDIA GPUs. So this is how we show our performance. How do we read this? Well, this is one setup on the NVIDIA A100 GPU with causal prefill attention operator. And we are varying the sequence length on the x-axis. On the y-axis, that's the performance. Higher is better, and it's all normalized relative to Neptune. So that's why Neptune is this green line here that always stay at 1.0. And you can see in this setup across all the sequence lengths, Neptune consistently outperforms all the other baselines here, including flex attention from PyTorch to Triton manually written kernels, as well as TVM, the compiler. Now let's scale this up to different GPUs and different operators. Here, 3 of the 6 prefill variance of attention operator, and across all the 4 GPUs, you can see Neptune still has, it's the same trend, right? Neptune gives you great performance and outperforms all the other baselines in most of the cases. And the same trend holds for the decode variance. Here's 2 of these 4, and you can see the performance gain is sometimes even larger on less optimized setups like AMD GPU. And you can see that again in this summary table, the performance on AMD MI300, we are getting almost 2x of speed up compared to all the baselines on average compared to over all these different operators, geomean average, by the way. So that's the evaluation. We have more evaluation results and more interesting details in the paper, and I encourage you to read that and figure out. What we did after the Neptune submission is we kept extending the system, and now we have an additional set of interesting results as well, including better performance on next generation GPUs such as Hopper and Blackwell as well, and I'm happy to talk about all of that after this talk. But in conclusion, data locality is critical and a difficult problem as indicated by flash attention. Neptune fixes this problem with its advanced fusion and improves locality, and Neptune loop plus tile optimization maximizes the performance. Therefore, Neptune generates high performance code on different devices for different operators. That's the end of my talk. I'm happy to take your questions.
All right, questions?
Okay, so if I understand correctly, the correction term is like a genericized version of the logic behind the online softmax correction. So in the flash session paper, they had to manually think through carefully the numerical stability implications of doing this correction. And so I'm wondering, like, do you have evaluation of that? And for this automation, how would you reason about the consequences numerically of doing this in the compiler?
I see. That is a great question. So what we have, I'll tell you what we have. We have proof of, well, correctness over real arithmetics, like you probably have guessed. That's by the way, that's basically the way Trader also did that in their flash attention. When they're proving the correctness of the repair term, they are doing that over real arithmetics, and then they reason about, well, they test the numerical accuracy on floating point numbers separately, and we did the same. So you can see here, this is also in the paper, by the way. We have a set of empirical study of the numerical precision of our kernel compared to the baselines, I mean, kernels from other baselines. And we are on par, sometimes maybe even a little bit better here compared to. Yeah, left is lower error, so that it's better. And you can find a full set of that result in our paper. So this is currently where we are at. We are empirically evaluating the numerical accuracy of the kernel, and it may be interesting future work to do this in a more analytical manner that is outside of this paper.
Great answer,
Thank you.
I think we have time for one more question. I mean, we're a little bit delayed because of the fire alarm, but I just want to make sure folks have a chance to ask questions. Oh, let's go, James.
Thank you. Great talk. Really interesting work. So there were only 2 cases there where you lost out to other compilers, and I was wondering if you had any intuition for those results, whether you investigated why you lost out.
Oh, which cases? Sorry, just 1 second.
So I think if you go back to your average performance, yeah, there were 2 cases on there where like there's 0.99 and there's 0.95, and I was wondering if you had any, like you investigated those cases and had any intuition why you lost out.
Right. So there are a couple of reasons why. Well, you can start setting up.
Readers from Chinese Academy of Science, Nanjing University, and North Carolina State University. We live in a sparse world. Sparse matrix vector multiplication, what you call SPMV, is one of the most important and fundamental sparse kernels. Because of the diversity of metric sparsity patterns, each of which requires a different tailored program design, auto-tuning is a very important way to improve SPMV performance. However, modern SPMV auto-tuners still face a fundamental dilemma, balancing performance and the search overhead. Current auto-tuners can be divided into two categories: template-based and template-free approaches. This slide shows template-based auto-tuners. The left side, format selector selects from predefined candidates programs for the input. The right side, compiler-based auto-tuner, includes predefined primitive combinations and tunes the inner parameters. Both the candidate programs and primitive combinations act as templates, which limits the performance potential. To overcome the limitation of template-based methods, we propose alpha sparse in 2022. It imitates human expert by breaking down the manual program design process into sequential steps. Each step is defined as an operator. As you can see in the diagram, by combining just 4 operators, alpha sparse can generate 3 fundamental SPMV programs from scratch. In terms of these example operators, the operator compress removes zeros from the matrix. The operator row blocking blocks the compressed matrix in row direction and map each part to a different computing unit. So then we can get a CSR format. The operator column blocking further block the matrix in column direction, and we can get COO format. Operator padding adds zeros to rows, so then we can get the ELL format. Today, alpha sparse has included 24 operators. They construct a huge template-free space, even including lots of potential new SPMV programs not covered by existing researches. So that it provides higher performance than template-based methods. However, the huge space comes with a huge auto-tuning overhead. Our goal is to develop an auto-tuner that achieves high SPMV performance and minimal search overhead. So we adopt search space of alpha sparse and use machine learning technology to accelerate search process. Using the machine learning to accelerate sparse auto-tuning is not a new idea. One common approach is matrix classification. This methodology first extracts features from input matrices and use the ML classifying model to map the input matrix to a specific category corresponding to a candidate program. It is lightweight, but is applicable only to format selector and unsuitable for template-free auto-tuning. To accelerate template-free auto-tuner like alpha sparse, the traditional machine learning approach relies on a cost model. In the perspective of alpha sparse, here is an example search space where every single point represents a specific operator combination, and we navigate this search space to find the suitable operator combinations for a specific matrix. The cost model is used to predict the performance of enumerated operator combinations and move towards the best design step by step. This requires evaluating a massive number of candidates. As a result, the overall search overhead remains high, time-consuming. This is the starting point of our thinking. But this brings us a fundamental question: why we must search? Can we just skip the iterative process and directly generate the best possible solution? This called for a new sparse auto-tuning methodology. bypass the iterative search by one-pass program generation. We reformulate auto-tuning as a sequential decision-making process. It predicts and appends alpha sparse operators one by one directly, construct the final SPMV program. Therefore, we cast our auto-tuning process as an instance of behavior cloning problem. Behavior cloning has been widely adopted in expert systems, including autonomous driving and game playing AI. It relies on 3 key concepts. First is the action, which denotes an expert's decision, like steering or braking in auto driving. Second is the action sequence, which is the series of actions required to complete a task. Third is the state, which captures the real-time context guiding each action prediction. In this way, we can map SPMV from auto-tuning concepts onto this behavior cloning framework. Actions correspond to alpha sparse operators. Action sequence respond complete SPMV program designs. And the state is the partially constructed program. By appending actions step by step, we can directly generate the optimal SPMV programs without any iterative searching. I think this methodology can not only accelerate SPMV autotuners like alpha sparse, but also other compilers who need to find the best pass combinations. However, this one-pass methodology introduced 2 new challenges. The challenge 1 is that we must shift to a real-time state-centric prediction. By construct, existing sparse autotuners are input-centric. They rely on static input information, which quickly becomes outdated as actions modify the matrix during iteration. To solve this, we used intermediate representation from our program generation method to serve as the dynamic state. Challenge 2 is the massive overhead of offline data collection. Because our model generates the optimal action sequence for each matrix, our training set must contain the absolute optimal sequence for every single matrix. Finding this is extremely time-consuming. Existing autotuners do not need to solve this problem, either because their search space are very small or because their dataset doesn't require the absolute optimal sequence for matrices. To solve this problem, we introduce a self-training mechanism. The background of our paper originates from our 2 previous works corresponding to the action and state spaces. This slide briefly introduces the action space, which is inherited from alpha sparse. Some of actions include tunable parameters. These actions allow us to change the matrix layout, map data to parallel processing units, choose reduction algorithms, and configure the kernel. If you're interested in them, please refer to alpha sparse paper. The intermediate representation of our code generator method is also introduced in our previous work, SR sparse. It has 2 parts, which is the middle layer transformed by actions to generate SPMV programs. The first part is matrix metadata set, which records matrix information, including layout, data mapping, and the extralarity data for reduction algorithms. Actions sequentially transform its content, and the metadata array used in kernel will form the final sparse format. The second part is the kernel skeleton. It maintains the code structure, including the position of loop structure and reduction algorithms. Actions progressively fill code into this skeleton to form the final code implementation. Now that we have introduced action and state, let's see how they came together to form the workload of online inference phase. First, the input matrix initialize the states. Next, ML models predict the next action based on the current state. Then, this predicts actions is applied to update the state. The loop repeats until the design is completed. Ultimately, the customized program is generated in a one-pass fashion. The key of online inference is IR-centric feature engineering. State features are extracted from the metadata arrays and the semi-completed kernel code. Unlike existing sparse autotuners that extract features from two-dimensional matrices, we need to extract features from one-dimensional metadata array. This is a difference. Thus, we introduce a fundamental operation called SIGStat. It applies a 1D difference filter to the sequential data and then compress the filter output into several matrices. We apply SIGStat to arrays related to matrix layout and the data mapping. This quantifies matrix irregularity and load balance. They are crucial factors that affect program design choices. For the kernel state, we record the previous predicted actions, which provide a compact summary of the code generated so far. Finally, we also introduce basic matrix features from traditional autotuners. Now, let's look at the offline phase. To address the massive data collection overhead, we adopt a multi-stage self-training approach. This process runs in several stages, with each stage processing 500 matrices, and we train our model between stages. We started with the seedling stage, which is heuristical strategy to collect initial data. Then we enter bootstrapping stage, which we use these newly trained models to directly generate ground truth data for the next 500 matrices, which saves search time. However, these early models acting as students might make mistakes. As you can see on the right side, blinding trusting the student's prediction might take the wrong path in yellow. To prevent this, we introduced a monitor as an error correction mechanism. It evaluates the student's confidence. If the confidence is low, the monitor expands the exploration range, shows as the red section, to safely captures the real ground truth in blue. Due to time limits, we are only highlighting the overall mechanism. For the details behind this, please refer to our paper. For evaluation, we use 150 matrices from the suit sparse matrix collection. The baseline are SOTA human-designed programs, autotuners, and sparse compiler. The performance evaluation shows that the sparse data achieves higher performance compared to all baselines, especially alpha sparse, which is the best baseline sharing the same search space. We think the main reason is that alpha sparse relies on ragged human-crafted rules, which is error-prone. In contrast, machine learning-based method of sparse data can capture the complex relation between matrix features and program design decisions. In terms of the inference time, sparse data reduce the search time from hours to milliseconds. This result shows the advancement of our one-pass inference. As you can see, the left side is alpha sparse. It takes over hours, but the right side is sparse data, which just takes milliseconds. That's conclude my presentation on sparse data. Thank you all so much for your time and attention today. Because of the visa issue, the first author cannot join there, and because some family issue, the last author, the corresponding author, cannot join as well. So I'm the middle one. So I will try my best to answer any questions from you, and if I cannot, I will forward them to the corresponding answer. Yeah.
Thank you. Yeah, let's take some questions. All right, well, folks, I don't think I see any hands right now. While folks are thinking about it, so a question I had is your last graph that sort of compares sparse, alpha sparse and sparse theta.
Yep.
Am I understanding right that part of the differences is that in sparse theta, you've done this kind of offline phase where you've collected a knowledge base, and that
Yeah.
is a little bit costly.
Yeah.
But then you can query that knowledge base very
Yeah.
efficiently here, basically.
For alpha sparse, you need to do iterative tuning.
Mhm.
Yeah, you need one profile and then go back to the compile and do again, and that's pretty time consuming. And another important thing is alpha sparse is a human guided one, so it can be easily biased.
Mm-hmm.
So that's why sparse data get a much higher performance comparing to alpha sparse.
Very cool.
Yep.
All right, any other questions? I mean, I have more. I think this work is incredible. I think there's so many moving parts,
Yep.
and auto-tuning versus learning. What is kind of the search space here? Because I mean, I think a big thesis of this paper is that you don't do auto-tuning.
Yeah.
How big is that search space? It must be big if alpha
Oh,
sparse.
we have 24 operators.
Okay.
In that search space, so the combination can be very huge.
I see.
Yeah.
And the question to sort of build off of that too, though, is sparse data is sort of like a one-time thing. It gets you a good implementation. Did you ever think that maybe that's a good seed, and then you could search around it in case your cost model found something a little bit different?
For the overall optimal setting, I would say alpha sparse might be the suboptimal, but it's comparable. Mm-hmm. Yeah, you might get 100 or 1% or 2% difference comparing to the optimal one, but to limit the search space and the time, you need to make choice between them. You need trade off between the accuracy and the search time.
Yep, the classic trade-off. All right, any other questions? If not, let's thank our speaker one more time.
Yeah, thank you.
And I think with this, that's the end of the session. Thank you, everybody, for joining. Thank you for dealing with the disruption of the fire alarm.
Lucian Popescu, who's going to tell us about CPP to Rust. Take it away.
Everybody, perfect. Thank you very much. I'm Lucian from University of Lisbon, and I want to present you C++ to Rust, the first automatic translator from C++ to safe Rust. Well, use after freeze and out-of-bounds memory issues. Those are errors you are all familiar with. They are 70% of the security vulnerabilities in software from Google and Microsoft. And we couldn't bring this number down for years. We've tried static analysis, hardenings, fuzzing, code reviews, trainings. None of them worked. In 2019, Google and Microsoft reported for the first time the 70% number. And in 2022, NSA urged people to switch to safe programming languages. While in the following years, the 70% issue still remained a problem. So, our current tools cannot bring down the 70% wall. We need to rethink the memory safety problem from the beginning. So, if our current tools don't work, let's try to switch the language. And this is exactly what happened in the industry, because people started to adopt memory-safe languages, which is good, because this eliminates an entire class of memory safety vulnerabilities by construction. However, this is not free. Google, for example, reported that for manually translating WOF2, a font compression library of around 4K lines of code, from C++ to Rust, it took 20 days, and in those 20 days, they added 20 bugs that were not present in the original application. So imagine this, 20 days and 20 bugs. We don't want to pay the same price for every rewritten application to save languages. We want to have automatic rewrites that take unsafe programming languages and go automatically to safe programming languages, so that you can push a button and get memory safety for free, without bugs, and instantaneously. And this is exactly what C++ to Rust is trying to achieve. Of course, we are not the first to try to solve this problem. C to Rust already exists, and it does a pretty good job at mechanically translating C to unsafe Rust. And it does this because, in general, it's undecidable to statically go from unsafe languages to safe languages due to program properties like pointer aliasing. In this specific example, safe Rust only allows one mutable reference at a time, but our original program contains two mutable aliases at the same time. So because C to Rust cannot fit this, let's say, safe Rust limitation, it chooses to generate unsafe code for the pointer handling parts, which is not ideal because we would like to have 100% safe applications, because even a small, tiny, unsafe block can compromise the security of the entire system. So to solve this problem, we created C++ to Rust, which is the first automatic translator from arbitrary C++ to safe Rust. And we managed to generate safe Rust from the beginning because we shift mutability and ownership at runtime. And let me explain you what I mean by that with the following example. So in the beginning, we wrap all local variables in what we call a value. This value is just a type alias over an RC ref cell of t. And remember the safe Rust limitation that allows only one mutable alias at a time. Well, we would like to have two mutable aliases at a time. And the RC layer allows us exactly this. Have multiple layers, and with ref cell mutate through all those aliases at the same time. So because we cannot feed the compile time safe Rust checks, we move the checks at runtime using RC ref cell of t, so that we can handle arbitrary C++ code. Besides this, we create a new type called PTR pointer, which is just a nice addition over the value model because it keeps a weak reference to an already existing value. And it also supports generic pointer operations, such as taking the address of a value using as pointer and dereferencing the value. And here inside deref is where the interesting things happen. Because on one hand, we need to check that the weak reference still points into a valid value. And on the other hand, we need to check that we can do mutations through the ref cell at that point in time. In this example, it's both checks pass, so the code is translated perfectly fine. This is the core of C++ to Rust, the value and the PTR types. These enable our safe Rust translation. And to better understand the differences between our strategy and the current strategies, take a quick look at this plot. We want to have applications that are both fast and safe. That's our goal. I think we can all agree on that. C++ sits on the horizontal line at the maximum speed. And through the years, people applied mitigations such as hardening, fuzzers, static analysis to make the safety better, right? But this also brings the performance down. So C2Rust come into picture, and well, it generates code which is as fast as the original code, right? Because the code that is generated is unsafe. And through the years, people have tried to make the output of C2Rust safer. But I'm afraid we cannot achieve 100% safety with this, because it's hard to reason about safe properties of the program, like ownership, in the presence of unsafe features like row pointers, for example. So we created C++ to Rust, which generates safe Rust code in the beginning. So as you can see, the code is quite slow because we had a lot of runtime checks to make sure that the properties of the program are still safe. And to fix this problem, we created a set of source-to-source optimizations that bring the performance of the Rust code, of the safe Rust code, as close as possible to C++. We are getting there. I'll present you in a few minutes the optimization that we make, but research is still needed to reach our fast and safe application. Again, C++ to Rust, our main bet on C++ to Rust is that it's easier to optimize for speed than to optimize for safety. Good. Let's go through a translation walkthrough. We have this beautiful piece of C++ code that we would like to transform to Rust. And I mentioned that we do mechanical translation. So we need a set of translation rules for types and for expressions in general, a function call in this case. And this is the generated Rust code. Don't try to understand it for now, because we will optimize it in a minute. But I wanted to focus on how we got to this code. So our translator is an AST visitor over the Clang infrastructure. So for every type that we visit, we query the translation database and well, emit the corresponding Rust code. And we do exactly the same thing for expressions. In this case, a function call of make unique. And again, this is the generated Rust code. The most important thing about it is that it's safe. It doesn't use any unsafe features. But as you can see, it's not idiomatic. No human being would write this. And it's definitely not fast, because it contains a lot of runtime checks. So to fix those two problems, we created a set of source-to-source optimizations on the generated code. And up until this moment, we are able to eliminate three constructs: RCs, ref cells, and options. And I want to present you what are the, let's say, preconditions for doing each optimization and how the code look at each step. Let's try to eliminate the RCs. The most important precondition for doing this is to make sure that nobody takes the address of the A variable. Remember that in our pointer model, we use a weak reference to an already existing RC. So if we drop the RC, we break the pointer model, which we don't want. But fortunately, in this case, nobody takes the address of A, so it's perfectly fine to eliminate the RC. Good. So the next step is the ref cell elimination. Conceptually, the most important precondition here is to make sure that the ref cell, the dynamic reference, if you want, behave exactly the same as a native Rust reference. And this only happens when borrow and borrow mute are called on this dynamic reference type. Borrow is used for reading, and borrow mute is used for writing. So in this example, only those two methods are used, so it's perfectly fine to do the optimization. We're getting there. The code looks more natural, let's say. And the final optimization is the option optimization. This is quite simple, because in Rust, option is a type that only has two valid states, some and none. And if we only assign some to the option, then the option layer doesn't make sense at all, and we can just eliminate it. And this is the final generated Rust code. It's safe, it's fast, and it's definitely more idiomatic. what you would expect from a good translator. So if you paid attention, I skipped a few optimization passes because after the option elimination on V, there is still a value, but we rerun the same set of optimizations until we reach a fixed point. And the fixed point is exactly the code below. So saying this, you can think of the middle code, the firstly generated code, as an intermediate representation that we progressively optimize in order to get to the final code. Very well. I hope you got a good understanding of our safe translation with the value in PTR, how we do mechanical translation, and what are the source optimizations. Because I would like to go into some numbers. We managed to translate two security-sensitive applications used in Google Chrome, totaling in 13K lines of code. One of them is WOF2, the font compression library that I mentioned in the beginning, the 20 days and 20 bugs font library. We managed to translate this instantaneously without adding any new bugs. And Brunsley, which is a JPEG repacker. They use a lot of interesting C++ features, a lot of STL, maps, vectors, queues, dequeues, stacks, unique pointers, a lot of those. A lot of OOP with inheritance, composition, pure virtual classes, void pointers for mem copying, mem setting, or just passing generics through functions. And Brunsley especially uses a lot of lambdas to define callbacks that are later passed to functions, or just deduplicate some small pieces of code inside the functions. So for both applications, we compared 3 versions. The original C++ version, the C++ Rust unsafe model. We developed this model only for benchmarking purposes, and the output should be more or less similar to the output of C to Rust. And finally, the C++ to Rust safe model, which is the default model, and it's exactly what I presented you earlier with the value pointer and the runtime checks. These are the numbers for WOF2. On the horizontal axis, there are the modes that I told you about earlier: unsafe, safe, safe plus optimizations, the source-to-source optimizations I showed you earlier, and the public data from the manual port. So, and on the vertical axis, there are the metrics relative to C++. And as you can see, for compression time, the numbers are quite flat. And this happens because most of the time is not spent inside our translated code. Instead, it's offloaded into an external crate called Brotli. So the performance impact is not visible at all. But for decompression, the things are a bit different, as you can see. We generate safe Rust code that is 7 times slower than the C++ code in the beginning. And this is exactly the strategy that we choose in the beginning. Generate safe Rust code in the beginning, accept that it's slow, then optimize it for speed. And as you can see, this is exactly what we did. We, using our optimizations, RC, refcell, and option, we managed to increase the performance by a factor of 2. The missing optimization here to bring the code as close as possible to C++ would be a PTR elimination and replace PTRs with native Rust references, mutable and immutable references, because that would clearly make the code faster and more idiomatic. But we are working on this. The memory usage numbers are quite flat as well. For binary size, we also managed to optimize it with our optimizations. And here, for lines of code, it's a bit interesting because Rust is a bit more verbose than C++, especially than the C++ style used at Google. Because, for example, Rust chooses to break each argument on a different line of a function, while the C++ style at Google chooses to fill an entire line with arguments, then break to the other one. Good, so this was WOF2, and this is Brunsley, which is 50 times slower than the original C++ code. And this happens because Brunsley has a different, let's say, profile than WOF2. It uses a lot of pointers to pass data in and out functions instead of returning pointers, and it also has some pointer-heavy loops. And because of that, there are a lot of runtime checks, which bring the performance down. But again, our current optimizer with RC, ref cell, and option increase the performance by a factor of 8. And again, the missing optimization is the PTR elimination. Memory-wise, we also optimize it because we get rid of RC and ref cells. And the numbers for binary size and lines of code are, again, quite flat. So these two applications, WOF2 and Bruce Lee, we managed to translate them to safe Rust without adding any bugs. And well, the performance is, we brought the performance as close as possible to C++. And this was C++ to Rust in a nutshell. It generates memory-safe Rust in the beginning, and it optimizes for speed to get as close as possible to C++. The project is open source, so please try it. Thank you.
All right, thanks for the talk. Let's give it to the audience for questions.
So if you take C++ code with some known bugs and issues and run from C++ for your system, which of them are detected on the compile time, which are shifted on runtime, and if they shift to the runtime, how the error handling is implemented, how they handled?
Yeah, so for well-behaved code in C++, it should have the same behavior in Rust. And for code that has undefined behavior, for example, we translate that to panics at runtime or to compile time errors. Yeah.
So one interesting thing I noticed in your example is that there's a call to a sum function that takes in a pointer, and it appears we just kind of believe that that's not doing any criminal activities. Generally, how do you make that assertion, and is it a global compilation argument? And if it's a global compilation argument, how do you reconcile that with the general approach that C++ uses for separate compilation?
I guess you're referring to the example here, right?
Yeah, there's a sum call there, and I just don't believe that I can trust that it was nothing interesting.
Do you mean the sum RC new, ref cell new, or?
Line 2.
Sorry.
What's the argument type of sum of the function?
Yeah, so in short, we only do intra-procedural optimizations. We don't look inside other functions, but this is not a fundamental limitation. We can do that, but it's just slower. So
and I think it doesn't take a pointer.
Yeah, sorry for that. It doesn't take a pointer. Yeah, we give up because, again, for the moment, we do intra-procedural, but it's not a fundamental limitation. We can extend that.
One last question.
Yeah, so I have a question about like the design decision, kind of. So from what I understand, we start with like adding these, let's say, boilerplates to the Rust translation, and with the claim that like we need to add this to ensure safety, and we try to remove the boilerplate where we know the code is inherently safe.
Yep.
But I guess like the main problem that we needed C to Rust translation was like the inherent unsafe C++ code, which when you like translate it into Rust still has the boilerplate, and probably that's why you still have like these performance problems, right?
Mm-hmm.
So I want to know like what are the plans for like, because I'm guessing like if somebody did some unsafe stuff in C++, it was because of the performance. And if they want their code translated into Rust, they want those unsafe parts to be taken care of, not the other parts, probably.
Yeah, makes sense. So our source optimization, let's say, feedback is also designed to be used by humans, not only by a machine to run automatically. So if you have some domain-specific optimizations that you want to do, you can freely do them so that you can recover the optimization, even if the default optimization, let's say, don't know about them. Yeah.
All right, let's thank Lucian again.
Thank you.
And for the next talk, if you are sitting close to the aisle, please move in a bit, because we have some people in the back that don't have a seat, so you can help everybody get a seat by moving to the walls and making the aisle seats available. Thank you. So the next talk will be by Victor Chen, who will tell us about a raffinator. Take it away.
Hello. Okay. Thanks. Today I'll be talking about Refinator, which is correct, precise, automated C to safe Rust interface translation that enables modular C to safe Rust whole program translation. So I'll start by motivating the problem and giving some background, and then I'll describe the specific interface translation problem that Refinator aims to solve. Then I'll describe how Refinator works to solve this problem, and then I'll show our evaluation results. So why do we care about C to safe Rust translation? Well, the C programming language is famously not memory safe. Memory safety bugs are encountered frequently, and they have an enormous real-world cost, as the last talk pointed out. So there is growing interest in transitioning away from non-memory safe languages like C and C++, specifically transitioning to safe Rust, which is memory safe and performant, and therefore suitable for similar use cases as C, at least for user programs. So one thing I would like to do is automatically translate C to safe Rust in order to remove memory safety bugs. Now, translating C to safe Rust turns out to be hard, and the central difficulty is Rust's strict ownership and borrowing rules, which requires precise whole program reasoning to satisfy. And in the wild, there have been two general categories of approaches. There have been mechanical approaches like C to Rust, which has been mentioned before. And, well, that produces horribly unsafe code, so that's not satisfactory. There's also LLM-based approaches, but if you use an LLM, you also get all the pitfalls of using an LLM. Namely, you need to verify that the output is actually good. Now, to address the difficulty of satisfying Rust's ownership and borrowing rules, we envision the following translation method, which is also the envisioned use case of Refinator. First, take as input a C program, and then determine a correct and precise safe Rust interface. For our purposes, an interface consists of struct definitions, global variables, and function signatures. And to determine a correct and precise Rust interface requires whole program reasoning in order to satisfy the ownership and borrowing rules. Then, once we have figured out a correct and precise safe Rust interface, we can translate all of the function bodies one by one modularly. Refinator is this first step, this whole program reasoning interface translation step. So what exactly is the translation problem that Refinator solves? Well, to understand that, we'll look at some of the challenges of translating a C program into Rust. So as an example, let's consider this linked list program, something famously difficult to implement in Rust. This consists of two top-level declarations, one struct, which is a linked list node, and one function, push, which takes in an integer and a pointer to node, and pushes into the beginning of the linked list after a dummy node. What we want is for those top-level declarations, the struct definition and function signature, we want to find a corresponding declaration in Rust. Another way of thinking about this is to find Rust types to replace all of the C types. Now, the challenge is that the Rust interface must be correct and precise. But choosing a correct and precise Rust interface is tough, because a single C type can plausibly map to many Rust types. The most egregious example is the pointer. In C, there's one pointer type, but in Rust, there are tons of different pointer types that behave differently in the context of ownership and borrowing, which leads into our definition of correctness. So we say that a Rust interface is correct if, given that Rust interface, there exists a safe Rust implementation that preserves the copying and aliasing semantics present in the original C program. Now, even though we only care about translating interfaces, the correct interface depends on what the possible bodies of the possible translated bodies are. So Refinator will translate an interface by reasoning about these possible translated bodies without actually doing the translation of the bodies. To understand correctness in the context of this example, I'll point out one way that the correct interface particularly the interface for node, depends on the body of push. So these are the C semantics that we want to preserve. In the body of push, the C code allocates a node on the heap, gets a pointer to it called n, and then copies n into list arrow next. In order to replicate this behavior in Rust, we have to contend with its ownership and borrowing rules. So a crash course on ownership. In Rust, all objects have an owner, and objects are dropped when its owner goes out of scope. And here, when n is initialized, it owns the node that it points to, and on this line, list.next equals sum of n, ownership is transferred from n to list.next. If you try to write a Rust implementation that avoids doing an ownership transfer, it's not going to work. It's not going to pass borrow checking. So this ownership transfer is necessary. And the necessity of this ownership transfer implies that the type of the next field of the node struct must be an owning pointer. In terms of potential Rust types, this rules out certain Rust types like references because you can't transfer ownership to a reference. But other types, such as this complicated option RC ref cell node, are okay. Now, in this example, it's possible to pick a single Rust type for the next field of node based on correctness alone, but that's not true in general. For our next example, we'll consider the list parameter of this push function. To choose a single Rust type for this, we also need to consider precision. So obviously, since in C we have a pointer to node as the type of this list, when we translate to Rust, we also must pick some kind of pointer to node. Correctness rules out some of these types, namely this immutable reference to node, because the body of push will mutate the list argument. But there are a bunch of other pointer types that are okay. What we would like to do is we would like to choose the simplest, least costly correct type according to some cost function. Refnator's cost function says that these two types, which involve dynamic borrowing, are correct but not precise, but this native mutable Rust reference is correct and precise. So that's our translation problem. Now let's talk about how Refnator solves that translation problem. First, let's look at the general architecture of Refnator. Refnator takes as input a C program and then converts it to an intermediate representation. This is a 3-address code-based representation, which is useful for generating constraints out of. And then based on this intermediate representation, Refnator generates a bunch of SMT constraints and then plugs these SMT constraints into an off-the-shelf SMT solver. In our case, it's Z3. And then the solver will spit out a assignment of Rust types to C types, and that gives us our Rust interface. Next, we'll talk about some of the technical insights that make this possible, and we'll look at what some of these SMT constraints generated by Refnator are. So the first technical insight is that in Refnator's IR, C types are encoded as type fragments. So occurrences of C types are enumerated, and these occurrences come from struct fields, function returns, variables, and R-value expressions. And then these C types are broken up into fragments. If you look at the very bottom R-value expression, n, this has the C type pointer to node, and it's split into 2 type fragments, the pointer part and the node part. Then Refnator finds an appropriate Rust type, or part of a Rust type, for each of these type fragments. The advantage of using type fragments instead of reasoning about entire types at once in the constraints is that this allows the constraints to be simpler. This improves the performance of the SMT solver, and this also allows for the level of indirection of whatever Rust types are inferred to be adjusted as necessary. Another technical insight is that the SMT constraints generated by Refnator consider pointer transformations. So when choosing Rust types, pointer types are allowed to mismatch in certain contexts as long as the transformation is allowed to rectify it. This allows more correct types to be used than would otherwise be possible. So this picture shows all of the transformations considered. There's a lot of them. And the details are in the paper. So with these insights in mind, Refnator generates the following 4 categories of constraints. 3 of these categories deal with correctness. These are consistency, semantic preservation, and borrow checking. More about these later. And there's one final category that ensures that precise types are chosen, and this is encoded using optimality objectives fed into the SMT solver. First, let's look at what a consistency constraint might be. So the consistency constraints ensure that the Rust types chosen are consistent with the C types in the input program, and that the Rust types chosen are consistent with themselves. So like you can't have infinite structs or stuff like that. An example of a consistency constraint is that all of the chosen Rust types must match the C types in the input. In this example, we have the signature of the push function, which takes in a pointer to a node and a 32-bit integer. So obviously, our pointer to node in C maps to some kind of pointer to node in Rust, and our 32-bit integer in C maps to some kind of 32-bit integer in Rust. Our next category of constraint is called semantic preservation. What that really means is that the copying and aliasing behavior in the input C program must be preserved in a Rust translation. So as an example of a semantic preservation constraint, here, if the Rust type of the variable n isn't a copyable pointer, then the bold purple R value expression must not transfer ownership of n. And this matters because in Rust, only certain Rust types can be copied, and for pointers in particular, you can't just copy any old pointer. Like in C, you can only do arbitrary copies with certain types. And this constraint falls out from these facts. First, n is used in this call to replace first, and then it is used again at the end of main. Second, if n cannot be copied, then the ownership of n may be transferred, depending on what you choose as the type of this R value expression on the Rust side. Third, if ownership of n is transferred at that purple R value expression, then we can't use n at the end of main. So we end up with this constraint. And since in this particular implementation, n is a box of node, which is not a copyable pointer type, the type of the Rust types of this R value expression are constrained. So we cannot use something like a box of node because that would force an ownership transfer and violate this constraint. But we can use something like a reference to node or a mutable reference to node. Our third category of correctness constraint is the borrow checking constraints. These effectively mimic the Rust borrow checker and ensure that the translation can borrow check. So background on Rust borrowing rules. First, an object cannot be mutably borrowed by more than one mutable reference at a time. And second, an object cannot be moved while it is borrowed. A constraint that's generated by a Refnator that falls out from these borrowing rules is that if list here is borrowed at this start point in the program, then the type of the purple R value expression inside this call is some kind of shared reference. In this particular Rust implementation, list is borrowed by sublist in the boxed region. Therefore, list is already borrowed at the start point, and this use of list must translate to some shared borrow. What this means is that the types of this R value expression on the Rust side are restricted. So something like node, a bare node, is not allowed because that would force an ownership transfer, and a mutable reference to node is not allowed either because that violates exclusivity of mutable references. But something like a shared reference to node or even a shared reference to ref cell of node is allowed. And that concludes our discussion of the constraints. Now, how well does Refnator work? So we evaluated Refnator based on 3 metrics. The first 2, correctness and precision, we've already talked about. And the third one is performance. Yeah. And for the performance metric, what we care about is how long Refnator takes to infer an interface, not its runtime performance. And we evaluated these 3 metrics on 9 benchmarks. One of the benchmarks is the program that we've been looking at in our example, and 8 programs come from CrustBench, which is a C to Rust translation evaluation suite. We evaluated the following 6 constraints for all 3 criteria, correctness, precision, and performance, and we evaluated these additional 3 for performance only. Now, out of all of the interfaces that we evaluated for correctness and precision, they were indeed correct and precise. Now, for performance, we saw something a little interesting. The analysis time, which is the time that it takes to generate constraints, was very low across the board, but the solving time, the time that it takes for the SMT solver to solve the system of constraints, was very large. It dominated. And we also noticed that this increased very quickly. So one example was Arbitrary, which is, this is a lab from CrustBench, and it's about 350 lines of C code, but it took about 20 minutes to solve. Okay, so that concludes my talk. In conclusion, Refnator is correct, precise, automated C to Rust interface translation that enables modular C to Rust whole program translation. Thank you.
All right, let's go to the questions. And yeah, I saw, but there's too many.
Hi, great talk. So you gave an example of a linked list in the first place. What if that were a doubly linked list? Would your translator, like, how would it handle that?
It would still work. So actually, it would use the same types. It would still use RCs of ref cells for both the forward pointer and the backward pointer. So yeah, it works just fine with a doubly linked list.
So I don't quite get one of your previous examples. Would you like just roll over a little bit?
Yeah.
So yeah, here the replace first function on the right-hand side is supposed to mutate the list, right? But you only have like an immutable reference here. So is it a successful translation, or what's happening here?
Let's see what's going on. So like one way that we can get so it could be a correct translation depending on what the type of list is or how the node struct is defined. So like it's possible to use interior mutability here to mutate the list even though it's passed into replace first as an immutable reference.
You just now mentioned that when translating doubly linked list, you also use optional RC. However, for reference counting, if there's a cycle reference, there's going to be a memory leak. Have you ever accounted for this problem?
So we don't specifically account for memory leaks. We don't have any guarantees that the translated interfaces will admit an implementation that's memory leak free.
Okay, then let's thank our speaker again. Looks like we are ready for the next talk. Awesome, so our next talk will be about Hayroll, and our speaker is Haoran Peng. Take it away.
Hello, Rustaceans. This is Haoran from University of Washington, and today I'm super excited to bring to you my work, Hayroll, a modular wrapper for translating C macros and conditional compilation to Rust. Hayroll itself is an acronym for Harvest Annotator for Using Regions of Lexical Logic, while Harvest is our UW Harvest team is our C to Rust translation team at UW. Yeah, why translate C to Rust? Skipped, thanks to CPP to Rust and Refnator. Now, why translate C macros to Rust? Existing transpilers, for example, C to Rust, state-of-the-art, lose macros and configurability during translation. It takes in unpreprocessed C, which have macro names, and configurable compiler flags. But after it's translated to Rust, you get the Rust that lose macro names and have only fixed compiler flags. This information loss that's happening during the process is due to them running the C preprocessor in advance. They didn't do anything bad, they just ran the C preprocessor, which erased all this information. Well, we don't really want that. And an example of, we decided that macros in conditional compilation is such an integral part of C. People use them to write everything from constant to like small implementations of min, max, all kinds of that things. We decided to implement Hero. Hero translates C macros into Rust functions or macros, and it also translates C conditional compilation into Rust CFG blocks. Hero is the first and, as of now, the only system that handles the problem. Here's an example of pre-preprocessed C and post-preprocessed C. So here we have a conditional range here and a statement macro together with an expression macro. It is not clear that the mapping relationship between each other until I highlight it for you. And a result of taking that pre-processed C as an input before your C to Rust translation is that you get the same problem on the Rust side. It's not clear which part corresponds to which part. If you want to rebuild them into macros, you first have to know which macros they're from. It's not clear until I highlight it for you. So that raises our first challenge, which is the source correspondence challenge. That is not yet the end of the story because we are still missing this conditional compilation range. The ifdev libmcs fpudez flag is entirely lost because during this run of the C to Rust, we didn't define this flag here. They didn't pass it to the preprocessor, so that's lost. Reasonable. But if you run C to Rust again with that, you can see it producing an entirely different software version with this line of code hard-coded into it. Imagine we have like 10 such flags. We're ending up getting like 1,024 different versions of the software, which is not what we really want. What we want, this raises the second challenge, which is this configuration explosion problem. What we really want here is just one version of software that is configurable and have all macros and conditional compilation rebuilt into the Rust native way. If we dive deeper into this problem, we will then realize why C to Rust decided to run the preprocessor. The root cause is that C preprocessor is a different language from C itself. This is a typical C compilation pipeline where you start with C macros, which are just strings, no more than strings. You run C preprocessor, it's going to get you the pure C string. And then the C parser is going to parse it into CAST. All of those transpilers work on the CAST because they are AST rewrites. But macros are defined all the way back here. They're just strings. This raises our third challenge, which is analyzing these bunch of strings requires an entirely different technique than analyzing an AST. This also raises a practical engineering challenge, which is if we want all these existing C to Rust translators, C to Rust, C++ to Rust, which we just seen, and maybe my C to Rust in the future, who knows. If we want them to all support macro, they have to also dump a bunch of logic that's unrelated to their AST handling into their pipeline. Very tedious. We don't want everybody to do this, so we decided to isolate this problem, building Hero as a wrapper around any macro-oblivious translator to make them macro-aware. Summarization of our challenges and our solutions. To isolate this problem, we built Hero as a wrapper. To do macro analysis, we made use of Mackie, an existing macro analyzer tool. To handle the configuration explosion problem, we wrote a symbolic executor, not for C, but just for C preprocessor. And for source correspondence problem, we developed an in-AST tagging technique, which we call seeding. These solutions either become a component in our pipeline or become a pipeline design itself. Hero architecture. Hero is divided into 3 layers: the conditional compilation translation layer, the macro translation layer, and transpiler layer. Each layer handles one of these important challenges and then passes the task down to an underlying layer for another different challenge. Let's start from the conditional compilation translation layer. We first send the C code through Pioneer symbolic executor, which tells you for each line of the code, what is the enabling condition, that is, the configuration flags combinations that's required to enable this line of code. Then that information is sent through the splitter, which splits one configurable software into many configuration-specific softwares that together cover each line of the original functionality. Then each one of these copies are then sent through the macro translation layer, where it first meets the Mackie macro analyzer. It tells us useful properties of macros. For example, are they statements or expressions? Are they syntactical? Are they hygienic? And with that information, we then send the C code with that information into Cedar, where it puts in AST tags, which we call seeds, into the original C code. And that part is then sent through the underlying transpiler, Cedar Rust here. They translate not only the C code, but also the seeds all together onto the Rust side. Then our Reaper will be able to recognize all these seeds, then rebuild macros into the Rust translation. That is then sent back to the conditional compilation translation layer, where the merger merges all copies of the softwares into one copy of configurable software. We will start layer by layer, starting from the Pioneer symbolic executor. So, motivation. Why do we even need symbolic execution for for analyzing C macros? C conditional compilation. Here's an example. Just by looking at this code snippet, can you answer me, to enable this conditional compilation, shall we just define this __ libmcs fu-des flag? Is that all we need? You will not be able to answer this question because I didn't show you all of that. But if you actually tried that, you will see GCC compile with this flag. It's going to tell you error undefined reference to this variable. Yeah, what is happening? What you really need to do is look at all the header file it includes. That's where you find you're not supposed to use this flag as a user, and you're supposed to use non-underscored version of the flag, which sets up this flag for you, and also a lot of other variables. This is to say that C conditional compilation requires global reasoning, because they could have nested flags or derived flags, or even arithmetic computations between flags, comparisons between flags, all requiring a symbolic executor to find out. With our symbolic executor, you will know that both of these conditional ranges are enabled by the same flag, which is not the internal flag. After that, we send that information into the splitter, which is in charge of splitting a configurable program into many configuration-specific programs that together cover every line of code. For example, for the code snippet on the left, how many different configuration combinations are needed to cover every possibility? There are 3 flags, and 2 to the power of 3 is 8. So you can totally do 8. Well, that's sound, but not very efficient, because remember, each of these combinations means a run of the entire underlying macro translation layer. We don't want it to happen, so we instead used a greedy algorithm, which is to try to satisfy the most deeply nested line first. So we issue a combination which is defined feature 1 and 2, which will cover line 1 through 4, and we'll be able to realize that it also happens to cover 2 more lines with no extra configuration needed. And by repeating this process, we'll be able to cover all the configurations with just 3 different combinations, which is much more efficient. Then later, we're going into the macro translation layer. We're first going to introduce the Mackie macro analysis. Why do we need to analyze these macros? What do we need to know about these macros? This sourced from the problem of a macro translatability problem. Hero doesn't translate all macros. There are some macros with really bad properties that we have to keep expanded. For example, well, C macros are really just string copy-paste, and you can do really crazy things with them. You cannot translate all of them to Rust. For example, you can define semicolon to a semicolon and use that to close every expression. Totally legal, entirely insane. We are not going to translate that. A lot of other examples are here, but these are the ones that we'll just leave expanded. They're not going to prevent the program from translating it. We're just falling back to what Cedar Rust does. And a category that has slightly better properties, but also steps onto one of these properties, they can be translated into Rust macros, but not Rust functions yet. The ones with the best properties, essentially function no macros. They can be translated into Rust functions. And how do we know these properties? We made use of Mackie, and also we modified it a little bit. It was able to capture these properties by implementing a hook in Client's C preprocessor, essentially align them to AST nodes that have these properties, if they align with AST nodes at all. Okay, then we're going into the Cedar Reaper part of our program, which is for solving the source correspondence problem. Remember, the ultimate goal of source correspondence problem solving is to know which part of the Rust code was from which C macro expansion or C conditional compilation range. We did it in a non-intuitive way. First, the Cedar is going to put in-code AST tags into the C code before the Cedar Rust translation. These tags are syntactically preserving. For example, here, a statement after seeding are still statements. They're semantically preserving because these extra statements are no ops. They do not do anything, and it can carry metadata. After the benefit of having these properties is that after Cedar Rust translation, you keep this kind of sandwich structure of seeds and its contents. So whatever this macro is translated into, expanded some unreadable range of things, it doesn't matter. It's still sandwiched by these two statements over here. So our Reaper will be able to pick up these tags and wrap them back into Rust, either macros or functions. That's Cedar plus Reaper. So for different kinds of AST nodes, the seeding technique is a little bit different. We just introduced seeding statements, which is quite easy, just sandwich the structure. For seeding expressions, it's a little bit more tricky, but we managed to do it. Remember these properties. We want them to be syntactically preserving. We want the entire thing to still be an expression. And we want it to be semantically preserving. We want them to be evaluated to the same value. And we want them to be able to carry metadata. So we end up using this conditional expression. Some people also call them Turner expression in C, where we put the string, the metadata, into the condition clause, which should always evaluate to a non-zero value, meaning it should always take this, the first branch. Second branch, we are just satisfying the compiler with something of the correct type that you shouldn't really go to. You should never be able to reach that. And after that's being translated by Cedar Rust, you get this if expression in Rust, something, you all know it, something very easy to pick up and recognize by the Reaper part of our program. Then we're back to the conditional compilation translation layer, where merger merges all these versions of the software together into one configurable version. We do not do it by unification, because that's very costly. Instead, we had the Cedar also put placeholder seeds for conditional ranges that are not enabled, that are not activated in these different versions of software. For example, the left version could have been processed with feature 1 enabled, and the right version was processed with feature 2 enabled. So by also putting these placeholder tags, our merger will be able to pair these flags and kind of like git merge, select the right version to put into the merge software, and at the same time, of course, put feature tags to it. Yep. So overall, Hero preserves abstraction and configurability in transpilation. Evaluation. We ran Hero on libmcs, zlib, and crustbench. On correctness, Hero passes all the tests that Cedar Rust was able to pass. On translator performance, we run at 500 lines of code per second approximately, which is 20 times slower than Cedar Rust, but this is a one-time effort. It's much faster than LMs. And with regards to coverage, this is a fraction of macros we're able to translate. So overall, we were able to translate over 50% of the macros in these 3 libraries. And there's a huge difference between different libraries because people use macros in very different styles. For example, in libmcs, this is a math function library, and they have very disciplined use of macros, basically math functions. So we were able to translate almost all of them. And in zlib and crustbench, there's a lot more non-syntactical use of macros, which we were not able to translate in the best way. We just left them expanded. But this doesn't mean we cannot translate their program. It's just that the macros are left expanded. Performance. Mackie, the macro analyzer, is taking up the most time because for each of these macro translation layer runs, it has to be invoked independently. And the Pioneer part, our symbolic executor part, took the number 2 most time. It has only to be run once per translation, but for programs with more configurability, it runs significantly slower. Yeah, so that is Hero. We translate C macros into Rust functions or macros, and we translate C conditional compilation into Rust CFG attributes. We open sourced Hero, and the C to Rust team is working on integrating Hero. You're welcome to fork us.
All right, thanks for the talk. We're ready for some questions.
Hi, thanks for the talk. I was wondering, so how do you ensure that the behavior of things like feature 1 and feature 2 are actually disjoint and not like influencing each other? Because there's sometimes, is that part of the symbolic executors?
Yes, that's part of symbolic executor.
And then the second question is, how do you keep all the garbage macros from being included in like a bunch of things that like maybe libc sets?
What do you mean by garbage macros?
Like,
do you mean the ones that are never used?
No, there's a bunch that are just like underscore libc and then like, or sorry, glibc, and then like they set things to tell you kind of like version gate the different library versions and stuff.
Yeah, so we had a flag that says like, what is the project, what is the boundary of your project?
Okay,
what is
so
the macros they're care about? So all the system ones or the ones that you don't define as a developer in your project directory, we don't care about that.
Okay, so it's only the ones that you include.
Yeah. So basically we're doing concrete execution combined with symbolic execution, and the part like the library one are concretely executed.
Hi. My experience, most open source projects will have lots of macros, and there'll be some configurations of the macros that where the system simply doesn't build. Maybe it has junk code inside an ifdef or something. How do you handle those?
So we have a whitelist mode, which also allows you to, tell the symbolic executor which flags you care about, you want to explore. If you don't tell it anything about a whitelist, it's just going to explore everything.
Well, I think what I'm saying is that sometimes there'll be like combinations of 2 or more macros where if, macro foo and bar are both defined, then, we don't know what's going to happen then.
I see. Yeah, a best practice for having this kind of macros in the C code is by writing if def A and B, then hash error. I know not everybody does that. Yeah. So this is something you need to tell our symbolic executor for us to know. Otherwise, nobody will know.
Thank you.
I enjoyed the talk.
Thank you.
I understand Rust's proc macros are unhygienic. Do you have any plans to use that to tackle unhygienic macros from C land?
Sorry, what macros in Rust are unhygienic?
Proc macros.
I don't really know that. But
okay.
if
Maybe
we
can
know there's
offline.
something we can do, but definitely we will.
Okay.
They're not really unhygienic, but not complicated.
So I'm curious about the merger phase. Different compilation options could cause the common code to translate differently to Rust, right? So what happens when the merger encounters common code that didn't actually get translated the same from C to Rust?
Sorry, can you repeat your question?
So like in this example, you have like separate code and then there's some common code with regardless of feature. If the C to Rust translator translates them differently, what happens in that case?
Well, we made it an assumption that for the common code part, the C to Rust translation is going to translate them into the same thing. But if they don't, we will issue a warning.
Okay, great. Thank you.
All right. Thanks for the Q&A. Let's thank our speaker again. So now we are moving on to the proving side of things with a talk about Verospell, the semantic foundation for Veros, by Travis Hans.
I'm going to tell you about our work on building semantic foundations for a Rust verification tool called Veris. So let's start with what is Veris. Well, like I said, it's a verification tool for Rust that allows developers to add specifications and static checks to Rust code, like here. Like this. Thank you. All right, hope I'm good now. Okay, so in Varus, these specifications are machine checked by a combination of automated theorem proving and manual proofs by the developer. Varus generally targets systems programming and supports concurrency, low-level data structures, and unsafe code, and it generally has competitive performance in the machine checking of these proofs. Varus is open source, and there is much open source code written in Varus, over 250,000 lines. Things that are verified in full or in part, such as memory allocators, OS components, and cryptographic protocols, among others. So with so much code relying on Varus, we might wonder, is Varus itself actually correct? And in fact, there's quite a lot in the trusted computing base of Varus, including Rust itself, the theorem provers that Varus relies on, Varus's own verification generation, and its trusted specifications for Rust standard library. So our goal in this project is to begin chipping away at the bottom of this iceberg with soundness proofs, though we're not going to be focused on any of these things on the slide right now. Instead, we're going to be focused on one of Varus's more unique features, which are called the proof-oriented types. So let me start by telling you what those are. To explain the proof-oriented types, I need to sort of orient you within the Rust type system in general. So within Rust, there's a spectrum of types from commonplace, easy-to-use types to harder, more unusual types. On the easier side of things, we have things like box, shared references, and mutable references, which generally enforce a fairly clean ownership discipline that makes things easy to reason about. So to be specific, I'll give you this little code snippet here. The function takes two mutable references. We assign x to 0, y to 10, and then we assert that x is still 0. Now, in Rust, these mutable references are not allowed to alias, and therefore this assertion is always going to be true, and Varus can check it easily. This takes advantage of a property that in the Rust community is often called aliasing XOR mutable, or AXM. But as I said, these are just the commonplace, easier to use types. Within Rust, there are a bunch of harder types that make use of interior mutability, unsafety, or both. So for those who don't know, interior mutability refers to the situations where you mutate data from behind a shared reference. So by definition, these are places where AXM is violated. So how does Varus reason about these situations? Well, Varus actually has its own set of interesting types that handle these situations, which are what we call the proof-oriented types. So two of them, p-pointer and p-cell, are just proof-oriented analogs of common Rust unsafe primitives. But the other proof-oriented types are what we call ghost types, which only exist to facilitate proofs, and they have no runtime impact and no physical layout. And this collection of proof-oriented types can be used to verify many of the Rust libraries. So in this sense, the various proof-oriented types are kind of more primitive than the usual Rust libraries. Let me give a specific example of one of these types, the p-pointer type. So here's a line that does an allocation, and you can see it returns two things: a pointer, which is the p-pointer, that stands for permissioned pointer. Well, you can just think of it as a normal pointer. The important thing about this type is that it comes paired with a ghost type called the points to, which is based on the concept of the same name from separation logic. This is a ghost type, and it allows us to reason about the value that is pointed to by the pointer. And it also acts as a permission that allows us to read or write to the pointer. So if we continue on with the example, I'm going to start by copying the pointer twice here. So we now have the two pointers that alias to pointer. And then we're going to write to pointer 1, and then we're going to write to pointer 2. So here I am wantonly violating AXM because we have two alias pointers that we're writing to both of them. However, in this example, we still have the points to, and the points to object is in fact uniquely owned throughout. And by doing this, we're able to ensure data race freedom, and it also allows reasoning about the value behind the pointer. The idea here is that we are still enforcing an ownership discipline but we're doing so through this logical proof world of ghost types, not necessarily in a way that is tied to the physical layout of data. So that's a proof-oriented type in a nutshell. Varus, in fact, has a bunch of these, and these are all, in fact, based directly on separation logic concepts. I just talked about the points to, which is based on the classic points to of separation logic. But Varus also has types that are based on more modern separation logics, especially the iris separation logic, and one type based on a more recent separation logic library called Leaf, which is itself implemented in iris. Okay, so these proof-oriented types don't come out of nowhere. They're all related to foundational separation logic concepts. But the incarnations of these types in Varus is still only informally related to these foundational concepts. So that's what we want to try to fix in Varus Belt. We want to try to actually formalize the essence of these proof-oriented types and the relationship to the Rust type system. So that brings us to our contributions in Varus Belt. What we do is we prove a soundness theorem for a model language lambda Varus that incorporates specifications for these proof-oriented types and has a Rust-like semantics and borrow-based type system that captures the central Rust features. And it's all mechanized in Rock. Just to clarify what we're not doing, we're not going to be verifying the Varus implementation itself or any of its dependencies. We're not going to verify 100% of Varus's axioms and assumptions or use a 100% faithful model of Rust semantics or type system. So we're especially just going to get the essence of the proof-oriented types and Rust type system. So to explain how we do this, let's start with some background on Rust verification. So let's start with Rust Belt from 2018, one of the seminal works in the Rust verification space, which defines a model language called Lambda Rust with a borrow-based type system. And it proves a type soundness theorem in Rock using the iris separation logic, which essentially says that a well-typed program does not go wrong. That's great, but unfortunately it doesn't work for us because the various proof-oriented types don't actually obey this property. So proof-oriented types, in order to be correct, require not only the normal Rust type checking, but they also require the checking of verification conditions. For example, in our snippet earlier, Varus has to check that all the points to objects align with the pointers that they're being used with. So unfortunately, this property doesn't hold. However, a subsequent result, the Rust Hornbelt work, builds on Rust Belt by augmenting typing judgments with specifications. And they prove what's called a type spec soundness theorem, which says that a well-typed program with a checked specification does not go wrong. And this is the sort of thing we need to do Varus Belt. So with Rust Hornbelt, we basically have a roadmap, translate Varus types into Rust Hornbelt style specifications, and then prove this type spec soundness theorem. And so that is basically what we do. And for the rest of the talk, I'm going to talk about two of the big challenges we have to overcome in order to do this. So there's two main ones. The first one is that the proof-oriented types of Varus have many complex interactions with shared borrows whose handling in Rust Belt is somewhat non-trivial. And secondly, Rust Hornbelt has a fairly sophisticated handling of mutable borrows, which then has non-trivial interactions with the proof-oriented types. So I'll talk about both of these, starting with the first one, shared borrows. So types in Rust exhibit a wide spectrum of behaviors when they're taken behind a shared reference. So again, I'm going to contextualize this within Rust before talking about Varus. So for example, if you take a shared reference to a box, this will always give you a shared reference to the underlying data. But if you have a shared reference to a mutex, this could give you a mutable reference to the data if you were to take the lock. And if you have a shared reference to an RW lock, you could get either one. And this is just a few of them. So to handle this, what Rust Belt does is it defines a unique sharing predicate for every type. And here are a few from the Rust Belt paper. You don't have to read these in detail. I'll give you the high-level points, which are these. The sharing predicates are all propositions in the iris separation logic, which allows the Rust Belt soundness proofs to be carried out in iris. The second thing is that to write these propositions, Rust Belt developed a number of novel mechanisms known as the lifetime logic. So for each type, you will have to sort of pick and choose from these mechanisms to write these sharing predicates. But again, Varus works differently, because in Varus, these kinds of types can be derived and proved sound by combining the proof-oriented types. So again, it's the proof-oriented types which are considered primitive for the purposes of this work. And the issue then is that since these proof-oriented types sort of capture all the complex sharing behaviors that the Rust library types do, we need a sort of more systematic, uniform approach to constructing these sharing predicates of all these proof-oriented types than the sort of ad hoc per type approach used by Rust Belt. So the idea here is that we're going to create a new version of Rust Belt's lifetime logic that has one unifying mechanism for shared borrows. And to do this, we're going to leverage something called the leaf separation logic, which I actually mentioned earlier, which provides a uniform framework for reasoning about shared read-only resources via what it calls a guarding operator. We rebuild the lifetime logic on top of this guarding operator, yielding our new leaf lifetime logic. Specifically, we represent all borrows by this particular expression here, where the funny arrow in the center is the leaf guarding operator. And it very loosely means that the left-hand side resource can be used as a kind of proxy for using the resource on the right-hand side in a read-only fashion. In this case, the left-hand side resource is what we call a lifetime token, which is part of the lifetime logic, and it indicates that the borrow named by alpha has not expired. And the proposition on the right-hand side, P, is just an arbitrary proposition. So this allows us to use P as long as the borrow alpha is alive in a read-only fashion. And from this definition, we can in fact actually derive all the complex properties of shared borrows that we need to in Varus Belt. Okay, so that's at a very high level the first challenge. Now I'll talk about the second challenge, which again is mutable borrows. So, right. So the challenge here is that Rust Hornbelt supports something called the Rust Horn encoding for mutable borrows, which has also been used by other Rust verification tools like Crusoe. And Varus very recently adopted this encoding within the last couple of months. But when we started the Varus Belt project, we knew that Varus wanted to adopt the Rust Horn encoding, so we knew that we wanted to incorporate it into Varus Belt from the beginning. Okay, what exactly is the Rust Horn encoding? So it is an approach to mutable borrows that involves prophecy variables. Specifically, a mutable borrow is encoded as a pair that includes both the current value being pointed to by the borrow and the prophesied future value upon expiration of the borrow. So the challenge with this is not mutable borrows per se, but the prophecy variables, because the prophecy variables can cause cyclic dependencies when used in conjunction with the ghost data. So there's a paradox here, for example, where we have a prophecy going in a circle where we're prophesying the future value of some ghost state, but the ghost state itself sort of captures the prophecy variable. And this quickly leads to a contradiction because you can define the prophecy variable in a way in terms of itself. And so this is a clear unsoundness. So to deal with this, we have, in order to properly specify these interactions, we need to update the encoding of Rust Hornbelt to properly distinguish non-prophetic data from prophetic data. And if we update the coding to make this distinction, then we can actually properly specify everything in a way that sort of enforces that there are no cycles, and then we can recover soundness and prove our theorem. So with these challenges out of the way, we can complete the goals of Varus Belt, which I'll remind you of now. So the main one is that we want to prove a soundness theorem for some language lambda Varus. In our case, our lambda Varus is just based on Rust Belt's lambda Rust, and our theorem is based on Rust Hornbelt's type spec soundness theorem, using the appropriate modifications to the methodology as I've just described. So Varus Belt incorporates specs for these proof-oriented types, and it has Rust-like semantics, of course, because it's building off of lambda Rust. And again, it's all mechanized in Rock using Iris. There's a bit more in the paper. So one challenge is the handling of cells and interior mutability, which, so you can read all about that. That turns out to be fairly tricky. We also identified one soundness issue, actually, in the specification of one of these proof-oriented types called local invariant. And we also were able to come up with a mechanism for fixing that soundness issue and prove our fixed sound. And finally, of course, in the paper you can read about the nuanced differences between Varus and Varus belt and limitations of that nature. And that's all I have for you today, so thank you.
Thanks a lot for the talk. Who has a question? Otherwise, I can also open the questions. So I was wondering, since you now seem to have like a new lifetime logic version 2.0, basically based on Leaf, would it make do you think it would be possible to kind of redo original Rust belt based on that without involving any of these proof-oriented types, kind of directly going for the Rust type soundness proof? And would that simplify things, or would it just move things around?
I'm not entirely sure. I think in some sense it might move things around. There are a couple limitations where things that are easy in Rust belt become hard, like the definition of sin and sync in Varus belt, or particularly sinned, is much more complicated than it is in Rust belt due to the presence of local invariant. So that might be difficult. So I'm not entirely sure. I think maybe there might need to be a little more synthesis between the Varus belt way of doing things and the Rust belt way of doing things before it's really we'll be ready to like redo the classical Rust belt.
All right.
Hi, thanks for your talk. Could you help me understand what Rust horn belt is? Is it a programming language? Is it a language that's known to be sound, and you're interpreting every Varus program as a well-formed Rust horn belt program, or is that understanding incorrect?
So Rust horn belt is a framework for proving the correctness of Rust verification tools, which is why we're using it for Varus belt, because that's our goal, is to prove. So Rust horn, it's basically the main goal of Rust belt, like I said, was to prove the soundness of Rust type system, and the main goal of Rust horn belt was to be a framework to prove the soundness of Rust programs that have specifications. And Rust horn belt is built on the same Lambda Rust programming language as Rust belt. Does that answer your question?
The questions, there we go.
Nice talk. I think one contribution you mentioned that you somehow formally define some invariant things in the Varus. I've noticed that you prove all the things in Iris, and Iris has its own resource algebra. Do you during the paper find any difference that the Varus cannot express, but we can do that in Iris?
Let's see. So you're talking about the resource algebras in Iris versus the resource algebras in Varus. Is that your question? So there is actually there are some differences with the resource algebras in Varus, because you can take references to the ghost state, which isn't really a thing in Iris, right? So you can have read-only versions of the ghost state, and so there are extra laws in the Varus version that correspond to what you can do when you have a shared reference to a ghost state. So actually, in some sense, I think the Varus ones, because they have these interactions with the borrowing system, are a little more expressive than the Iris research algebras. And then the Varus storage protocols are an even more expressive version of the resource algebras that do even more things with shared borrows.
I have one quick last question while the next speaker sets up. If not, well, then let's thank Travis again. Right. So the final talk for this session will be about pure borrow, taking ideas from Rust into Haskell, and our presenter is Yusuke Matsushika.
Okay. Wait a minute. Okay. Hello, everyone. I'm Yusuke Matsushita from Kyoto University, and my collaborator is Hiromi Ishii from JIJ. Today, I'm thrilled to talk about our work, Pure Borrow, where linear Haskell meets Rust-style borrowing, or maybe how Haskell can make better friends with Rust. To start with, I show you the big picture of this work. Software is the art of using computers to embody human ideals. This leads to two major programming paradigms. Imperative programming, geared towards computers, and functional programming, designed for human reasoning. Programming languages have evolved to unify these two paradigms, yes. A key language on the imperative side is Rust, which you have heard of a lot in this session. So roughly speaking, it comes from C and C++, and adding ownership types for high-level safety and robustness. And in a sense, this is moving towards functional programming, I would say. And another key language on the functional side is Haskell. Haskell is special in that it strictly guarantees purity. What's it? A program is pure if it gives the same result regardless of the timing of computation. So, it's like the computation going in the Platonic world of mathematics. Notably, purity is vital for predictable parallelism or concurrency, and also lazy evaluation. Recent exciting news is the birth of linear Haskell, or Haskell extended with linear types, which is a kind of simple version of ownership type. This allows safe mutation inside pure computation and moving towards imperative programming, in a sense. So our work is going towards unifying the two paradigms, but can we go further? A key feature of Rust is borrows, or borrowing. It's a tricky feature to explain, but at a high level, it enables mutation without directly passing around ownership. So now we are ready to ask our core question. Can we safely and smoothly support Rust-style borrows in linear Haskell, especially preserving purity? We answer this question affirmatively with our work, Pure Borrow. At a high level, it enables purity, flexible mutation, and parallelism at the same time. Also, we have a case study of parallel quicksort to demonstrate. And it's implemented just as a set of APIs in linear Haskell. It means that it readily works on the existing Haskell compiler, GHC. And furthermore, we have a meta theory for Pure Borrow focusing on the purity. To be frank, it's still kind of a work in progress, but it already has a crucial insight, I would say, which is a history-based model of borrowing that justifies purity. So here is a high-level comparison of Pure Borrow with existing work. Compared with Haskell's core pure computation and SD monad, and Rust and basic linear Haskell, our Pure Borrow supports purity, mutation, and borrowing, parallelism, and leak freedom all at the same time. Okay, now we are ready to go into more technical details. First, I briefly review linear Haskell. In the original Haskell, data should be persistent for purity, and this can cause a lot of copying and mutation. For example, let's think of an operation that updates one element of the vector. This works like this. Unfortunately, we should also keep the original vector. So we end up copying the whole vector, which is bad for performance. Linear Haskell solves this by introducing linearity, which enables mutation in place. For example, the vector update operation can be typed like this in basic linear Haskell. Here, the lollipop arrow is the linear arrow, which statically enforces the argument to be used exactly once. Thanks to this, we no longer need to keep the original vector, and we can safely use in-place mutation. Great. However, this basic style still requires you to directly pass around ownership. Can we do better? We can take an idea from Rust. Rust style borrowing. When there is a fully owned object, we can borrow it to create a mutable borrower, which temporarily gets ownership of the object, and a lender, or temporarily frozen owner. A key idea is to upfront decide on the lifetime or the deadline. During the lifetime, the mutable borrower can freely mutate the data. Remarkably, we can also split a borrower into smaller borrowers that borrow disjoint substructures, each of which can freely perform mutation. And finally, after the lifetime ends, the lender can safely reclaim the ownership of the object with a new updated value, which results from a series of mutations. Crucially, there is no direct communication from the borrowers to the lender for all this. This makes Rust style borrowing so special. Cool, so we want this in linear Haskell, and can we really do that? We answer this question affirmatively by our work, PLDI. It introduces Rust style borrowing to linear Haskell, remarkably just by adding a number of APIs to linear Haskell. For borrowing, we have this simple function, borrow. This linearly turns an old object into a pair of a mutable borrower and a lender. Lin here is a witness that the computation is going in a linear context, about which we don't go into detail in this talk. During the lifetime, the borrower can freely mutate the data by various functions, including this modify that. Here we see the BO monad. This is a key mechanism we introduce, which I explain later. We can also split borrowers, for example, by this function, split at, which splits a vector borrower at an index. And crucially, you can drop or discard a mutable borrower at any time. Finally, after the lifetime ends, the lender can reclaim the ownership using this simple function, reclaim. The type class end alpha tells you that the lifetime alpha has ended. This might look simple, but actually quite magical, because we get the updated object without direct communication from borrowers to the lender. Our meta theory, which I explain later, justifies this. I briefly note here that our API design took a lot of inspiration from Rust-built separation logic model for borrowing. But we also want to emphasize that we solved various unique problems for Haskell. Now, I explain the BO monad, a key new concept we introduce. BO alpha A means a computation of A that is allowed only during the lifetime alpha. This is used to enforce the timing constraint for borrowing, saying that each access by a borrower should precede the lender's ownership reclaim. Crucially, the BO monad can be run in a pure computation using this function, run BO. A key trick here is a rank 2 polymorphism to take a fresh lifetime alpha. This can actually be seen as a rich variant of the ST monad, an old, well-known technique to embed mutation into pure computation. And also remarkably, the BO monad supports parallelism with a simple function, parBO. It just takes 2 BO closures and executes them in parallel. Despite non-determinism by concurrency, parBO keeps the purity. This is because linearity guarantees the disjointness of mutations. As an advanced topic, I briefly explain sharing and reborrowing. We can temporarily share a borrowed object with this function, sharing. The type share stands for a shared borrow, which has only read access, but can be freely shared, just like in usual Haskell. And here, this is thanks to the nonlinear arrow used here. A key technique used here is to take the lifetime intersection with a fresh lifetime beta to have a shorter lifetime. We can also reborrow a mutable borrower, which keeps a mutable borrower instead of a share borrower. Actually, sharing can be derived from a combination of reborrowing with this function share. Here, UR stands for unrestricted, which means nonlinear, and thus shareable. So this way, PureBorrow supports quite a rich set of features for Rust die borrowing, and further enables flexible combination of them thanks to Haskell's expressivity. Okay, now let's solve real problems. We conducted a case study of implementing parallel quicksort with our PureBorrow APIs. Here's a simplified code for our parallel quicksort function with a little idealized notation. By the pivot swap function at the 5th line, we can swap elements of the vector around the pivot value chosen for sorting in place. And this performs in-place mutation. This works in the BO monad, as you might notice. And by the split at function at the next line, we can divide a mutable borrow. And finally, we can recursively call qsort over each subvector and parallelize this with the parBO function. So this way, we enjoy performative parallel in-place mutation. As an advanced topic, to achieve better parallelization, we also implemented the work stealing scheduler, notably as a general purpose library extending PureBorrow. Please refer to the paper for details. In result, our parallel quicksort implementations successfully outperform the naive sequential implementation. But our point is rather that PureBorrow is a useful abstraction for safe parallel mutation. As a scientific contribution, we built a meta-theory that works towards proving the purity of PureBorrow framework. The main challenge is how to justify the ownership reclaimed by the lender, which happens without direct communication from the borrower to the lender. Our solution is simple but new. The key idea is to build operational semantics on a history-based model. Because every mutation on borrows is performed inside the BO monad, we can let the BO monad record the past mutation histories behind the scenes. And the BO monad can pass the whole history to the end lifetime token, which can be used by the lender to restore the updated value when it reclaims the ownership. Our main theorem says that our history-based operational semantics is strongly confluent or satisfies the diamond property over the choice of thread scheduling and evaluation order. One caveat is that we have not fully proved the purity in a sense in terms of referential transparency. This is because our semantics can generate fresh borrower IDs. Also, we should say that correspondence with this history-based operational semantics and standard memory-based operational semantics is quite a work in progress. Currently, we roughly sketched the proof strategy for progress by simulation by designing a dynamic relational linear type system, and completion of this proof is left for future work. I also want to briefly discuss a related work, OCaml, whose high-level motivation is similar to ours, but it's designed to require only lightweight annotational modes. This is great, but due to this, they only support core notional lifetimes, and they don't have purity. One interesting point is they distinguish linear and uniqueness. And we would like to say that like our borrowing is actually a kind of non-aliasing in their sense. Please refer to the paper for details. Lastly, you can find our ViaBorrow bucket library on Hackage, and you can use it without any tweaks on GHC, so please give it a try. So this is a summary of this talk with a big laugh. Thank you.
All right, thanks, Yusuke, for the talk. Who wants to ask a question?
Hi, very nice talks. Thank you very much. So I've noticed that in a lot of functions here, like modify add and pivot, they all take immutable reference and argument, but then return it. While in Rust, you usually would not return it. You don't need to. You automatically get it back. So what is missing there?
Thanks for a great question. So, so it is possible to like not to return the mutable reference. But if we do so, we would need to use a reborrowing function manually. Like basically, we should do lifetime management quite manually in Haskell because we don't have borrow checker. So this is kind of like workaround to deal with the lack of automation in Haskell.
Maybe in the same vein, I noticed you have an explicit drop function for mutable references. So like that, does Haskell not have affine types that you can drop automatically?
Yeah, exactly.
Do you think there's a chance they would add them to make this kind of stuff nicer?
So that's actually a very good question, and I asked like linear Haskell people if they can add affine types, but it seems that like it's kind of make type inference difficult because they support linearity or polymorphism or something. And if we add affineness, then the kind of algebra for like linearity, affineness, non-linearity forms quite like very tricky thing. So it seems that it's not easy to support for a while.
Okay, that brings us to the end of this very rusty session. Thank you all for coming, and let's thank Yusuke one more time.
me now? Okay. So I'm Mike Bond from Ohio State, and thank you for coming to this final session, PLDI. And we have 4 great talks today. The first is about revisiting partial tracing for GC. It will be given by Jong-Hoon Kim.
Yep. Yeah, thank you for the introduction. Hello everyone, I am Jung-Hyun Kim from KAIST. Today we will talk about our work, revisiting partial tracing for safe, efficient, and concurrent garbage collection in unmanaged languages. Modern softwares are Yeah, then I will start. Okay, hello everyone again. I'm Jung-Hyun Kim from KAIST. Today we will talk about our work, revisiting partial tracing for safe, efficient, and concurrent garbage collection in unmanaged languages. Modern software runs on more and more cores, so lock-free concurrency is now everywhere. It is great for scalability, but it is tricky to get right. Suppose we have a lock-free linked list on the heap. A reading thread, mutator 1, traverses the structure to find the key. And here it is accessing node B. While mutator is still using B, another mutator unlink B and frees it. Because nothing handled this reader-reclaimer race, the reader now touches freed memory, and we get a useafter-free error. The hard part is that this race has no compile time solution. Unlike single-threaded code, B has no static owner and no static lifetime for the compiler to reason about. So safety has to be decided at runtime. Managed languages like Java and C# already solved this. The compiler and runtime cooperate to provide an ideal environment for garbage collection. And we can see why using three criteria. First, it is efficient because compiler inserted save points let the runtime coordinate GC paces with low overhead. Second, it is safe because stack maps tell the collector exactly where the pointers are, so tracing is precise and never frees a live object. And third, it is easy to use because the programmer writes no manual reclamation at all. So managed GC wins on all 3, but only because it can lean on the compiler and runtime. Unmanaged languages such as C, C++, and Rust have no such support. So people usually manage memory by their own hand. The standard manual approach, epoch-based RCU, explicitly tracks in-use pointers. It protects a pointer before use and retires it to reclaim. On the efficiency criterion, this is excellent with very low mutator side overhead. But on the other 2 criteria, it fails. Manual tracking is well known to be error-prone, even for experts, because protecting or retiring at the wrong moment breaks the whole program. So it is both unsafe and hard to use. These are real useafter-free bugs from widely used Rust concurrency libraries. So even in unmanaged languages, automatic GC is highly desirable. Some automatic GC techniques already exist for unmanaged languages, and we can review them with the three criteria. They fell into 2 families, conservative tracing like BDWGC, and reference counting like circ. But unfortunately, both are not efficient. And each one traces away either safety or ease of use. Let's see why one family at a time. Take conservative tracing first. It is inefficient because lacking compiler support, it suspends every mutator with OS signals to get a consistent snapshot. That makes the program about 89% slower than the manual reclamation. And it is unsafe because without stack maps, it scans raw memory word by word for pointer-like values. When a live pointer does not look like 1, that false negative leads to use after free. But it is easy to use. Once it identifies the roots, it traces everything reachable, so it handles cycle for free. The other family is reference counting. It is inefficient because the count must be updated constantly. For example, as a mutator traverses the list, every single step atomically increments or decrements counts. Even the state-of-the-art Circ is a recent scheme that optimizes this, but it is still about 55% slower than the manual reclamation. So the overhead of reference counting is quite fundamental. It is safe though, because an object is freed exactly when its count hits 0. But it is hard to use because a reference cycle like E and F pointing to each other keeps the count positive forever. So the programmer has to break such cycles by hand. To wrap up the problem, both families fall short, and the gap is clear. No existing garbage collection in unmanaged languages is efficient, safe, easy to use at the same time. And this is exactly what we deliver. Concurrent deferred partial tracing, a concurrent garbage collection library in unmanaged languages. Our idea is quite simple. Use reference counting only for the roots and tracing for the heap. First, we reference count just the root objects, the ones reachable from the outside the heap. Then, starting from those roots, we trace it through the heap. This design is safe because the reference counts identify the roots precisely without no fragile conservative scanning. And it is easy to use because tracing the heap still collects cyclic garbage, which has no external reference. So safety and ease of use come for free. But interestingly, this idea itself is not novel. A classic paper from 22 years ago already conceived this hybrid design and named it partial tracing. So the only criterion still in question is efficiency. And here's the catch. Partial tracing has long been considered inefficient, which is why it was never adopted into a concurrent GC. That inefficiency has two sources. First, the original design coordinated its GC paces with a stop-the-word pass that suspends every mutator. Second, like reference counting, it constantly updates counts for root pointers, even though we count only roots. The roots themselves change all the time during traversal. And this is exactly what we fix. Our contribution is making partial tracing efficient through a highly concurrent design. For the stop-the-word pass, we make tracing concurrent with a stop-the-word-free mark-sweep design. For the high RC update cost, we follow the classic wisdom of deferred reference counting, which amortizes the cost of root updates. Together, these gives all three criteria at once. In this talk, for the time, we will focus on the first one, the concurrent stop-the-word-free mark-sweep design. First, some preliminaries on how the mark paces of mark-sweep GC work. There are typically two. The first pace is tracing. The collector marks the root, then traces the heap by draining mark stacks. In a concurrent setting, those mark stacks are distributed across threads. And the collector or the owning thread pops a task, marks it, and pushes its children until the stacks run dry. The second phase is completion. When the collector believes that no live objects are left to mark, it scans every mark stack, and if they are all empty, tracing is done. But once concurrency comes in, this is not so simple, because mutators help with tracing too. So a mutator and the collector can touch the same mark stack at the same time. that creates two data races, and both prematurely complete tracing. First one is late push. Suppose two nodes, one marked it and one not, and two threads run, the collector and a mutator. The mutator holds the only reference to B, so it tries to push B onto its mark stack. But before that push finishes, the collector scans, sees the stack empty, and concludes tracing is done. In this case, B was never marked, so it is freed while still being reachable, a user-free error. The second is early pop. Again, the mutator holds the only reference to node B, but a mark task for B is already on the stack. The mutator pops B to process it, which empties the stack, and it starts to mark the node, but before it finishes, the collector scans, declares tracing is done, B is freed, the same, user-free. The textbook fix is a stop-the-world pass. In both cases, the mutator finishes its stack operation before it hits a GC save point. So the collector only scans once the scans are consistent. This is correct, but it poses every mutator at save points to transition paces, and that serialization can cause a scalability problem. So we replace it with two concurrent mechanisms, pace consensus for the late push, inspired by epoch consensus, and concurrent validation in the completion pace for the early pop. Let's start with late push and pace consensus. The approach is to order every mutator push before the collector scan, while keeping the mutator side lock-free. The collector periodically advances a global epoch, which is a pair of a timestamp and a pace, stepping through normal, tracing, and completion pace. At each pace, the collector initiates that pace's critical collection work, such as tracing the heap or scanning the stack. On this foundation, each mutator opens and closes a pace critical section, and inside, it freely traverses the heap and creates a new RC pointer. Inside that same section, a mark task can be pushed to or popped from the mutator's own mark stack. This pace consensus then gives us the happens before relation we need. A push inside the critical section during the tracing pace completes before the collector scan during the completion pace. So any mutation of the mark stack is always visible to the collector before it can conclude tracing. Concretely, the mutator is tracing inside the critical section during the tracing pace. It is about to push B. Meanwhile, the collector wants to advance to completion and scan. But it first waits for the mutator's open section to close. The mutator pushes B and ends its critical section. Now the collector scans and finds the stack not empty and resumes tracing instead of freeing B. Now the early pop, which we fix with concurrent validation. The core idea is a modification timestamp that captures a concurrent pop, and the flow graph on the left is the validation loop. From completion, we either succeed back to normal or fail and retry. First, during the tracing and completion pace, a mutator stamps a modification timestamp on a stack before it modifies the stack. Second, during completion, the collector does a double-checked read, like a sequence lock. It checks that all stacks are empty and that no stamp matches the current timestamp. Concretely, the mutator is in a critical section during completion with B on its stack. Before it pops, it stamps the stack with the current timestamp, T+2. It then pops B and tries to mark it. When the collector validates, the stack itself is empty, but the stamp equals to the current timestamp. So the check fails and the collector resumes tracing. Putting all of these building blocks together, CDPT becomes the first scheme to get all three criteria at once: efficiency, safety, and ease of use. And we backed that efficiency claim up with micro and macro benchmarks. First, for the micro benchmark, our target is lock-free maps. Multiple threads call get, insert, and remove call while we scale the thread count up, which is the workload that stresses reclamation hardest. Our most striking result is tail latency. Among the automatic schemes, CDPT keeps the tail latency by far the most stable. At the far tail, the P99.99, CDPT cuts latency about 6 times compared to reference counting, and about 32 times compared with conservative tracing. Throughput tells the same story. CDPT in red outperforms both automatic schemes in purple and blue, and stays comparable with handwritten reclamation, all while remaining fully automatic. The one honest trade-off is memory. Because CDPT traces the heap before collecting, it uses more memory than manual baseline, but it stays well below the other automatic schemes, so the overhead stays reasonable. Finally, to show this holes beyond a micro benchmark, we turned it to Mocha, a production-ready Rust cache library. We ran the YCSB benchmark, and we replaced Mocha's handwritten epoch-based reclamation with our CDPT algorithm. That removed every manual reclamation call and unsafe access block, a net reduction of 120 lines. The result is that on workload A, throughput moves by about 0.25%, and P99 latency by under 1%, both within noise. So in a real-world application, we can swap a handwritten reclamation for our automatic one with no visible performance penalty. Yeah, so to wrap up, CDPT revives partial tracing as a concurrent GC library that is efficient, safe, and easy to use. The paper has much more details, such as optimizing local routes using hazard pointers, and hybrid write barriers for correctness, and type-safe Rust API, and even more. And everything is open source at the link on the right. That's all, and I'm happy to take any questions. Thank you.
Thank you, very nice talk. So how would you differentiate your work from taking one of those already existing concurrent GCs, for example, Ghost GC, or there's lots of Java GCs out there, implementing in Rust and comparing that to your work? Like, what differentiates your work from all existing GCs?
So first of all, thank you for the good question. And as I said in the early slides, those conventional garbage collector relied on runtime and compiler. And in those many languages, those garbage collector needs GC save points and precise tag maps to work correctly. But in our setting, those kind of infrastructure doesn't exist. So basically, we need to find another approach, and our work is one of them. Yeah.
I see. Thank you.
Oh, yeah.
Question? Yeah, quick follow-up to that one. What about with Rust? When you're supporting Rust, that is, because there, in principle, at least, you do have stack maps and so forth, in principle,
so,
in LLVM.
So are you mentioning some LLVM experimental feature like stack maps?
Yeah, I just mean that when you've got a well-typed language, for C and C++, it makes, what you're saying makes complete sense, but once you get to a language like Rust, in principle at least, it's a different story, right?
Yeah, so I guess that approach will require accessing the compiler level knowledge. So I think that will have a trade-off, but our approach is purely library-based, and yeah, and which is portable to other code base very easily. Yeah, thank you.
Time for one quick question. All right. Thank you.
Yeah, thank you.
The second talk in the session is about dynamically checked deep immutability in Python. It'll be given by Fritjof Stoll.
All right. Hello, everyone. So this talk is about dynamically checked deep immutability in Python, and it's work with me and the lovely people you can see up there. So immutability has been well studied by our community, right? It gives us the ability to reason about programs better, it allows optimizations, and it allows us to share stuff in concurrent setting without needing synchronization. As such, it's also employed in many languages. Common ones are functional programming languages. Here I have, for example, Erlang or Clojure, and here immutability is deep. Deep meaning that if we have one object that is immutable, all objects reachable from this object also have to be immutable. And in functional programming languages, this is often enforced by simply having no mutation operations. So if you have no operations that can mutate stuff, ergo you don't need to enforce it. Then we have languages like Rust, which we've just heard about, and Pony. And here you also have deep immutability, but this deep immutability is enforced by an ownership model. Then we have imperative languages, take Java and C++, where we have shallow immutability. And shallow immutability meaning that we can have an immutable object that actually points to mutable ones. And here it's often enforced with a type system and the support of keywords like final and const. And then we have Python, right? This is what this talk is about. And Python kind of doesn't have a concept of immutability. There are some objects which have some enforcement, but there is no global concept, and therefore also no real enforcement. And this brings us to what we've done. So we have designed deep immutability for Python with a specific goal of sharing data across threads. And with this, we've achieved a beautiful graph over there, and I'm going to tell you the journey how we got there. But to highlight is that the blue graph is what's possible on current stable Python, and the orange one is what we've achieved. And we've also found generalizable concepts. So if you, in your language, want to add dynamically checked deep immutability, these will be super interesting to you. This is, for one, feasibility. This is a way to control if and how objects can become immutable. And detachment, a way to control and prevent immutability from propagating too far. Now, some of you looking at the graph may wonder, isn't Python non-concurrent? Isn't that what a lot of discussions are currently about? And it turns out that Python currently has a global interpreter lock. So whenever the interpreter tries to execute some bytecode, it has to acquire this lock. But there is a push from the community to change this, or at least make Python more concurrent. One of the best known ones is free-threaded Python. This is currently experimental, and this one is basically, what if we remove the GIL? But there's also a proposal of subinterpreters. And this proposal is actually stable since Python 3.12. And subinterpreters allow you to run multiple interpreters in one process, but critically, nothing is shared. This is isolated interpreters. Let's look at this in a little bit more detail. For this, we have our single Python process here. This is your proper, usual, single-threaded Python. And this beautiful process can create mutable objects like every other day. But with the addition, or with subinterpreters, it is possible to spawn a second subinterpreter with a second thread running. And the important part is they are completely isolated. It is not possible for interpreter 2 to see the objects of interpreter 1. This is cool on the concurrency perspective because you don't need synchronization, but it makes communication hard, right? So in stable Python, what you have to do is you have to manually copy all data over, which is not necessarily efficient. So this is where immutability comes in. If we can turn these objects immutable, annotated as this ice blue in this presentation, then we can, in theory, share these objects across two subinterpreters without needing synchronization between the two of them, right? Because the objects are immutable. There's nothing to synchronize about. So our goal with this work was to enable sharing across subinterpreters. And we also wanted this to be sound. We needed this as a language level construct to allow us reasoning about it and for the runtime to support this, for example, also the direct sharing. But we are not designing this in a vacuum, right? We have certain restrictions. And the first one is Python doesn't have a type system. So we can't rely on existing immutability designs and have to do something that works for Python. And then there's also the problem that Python has a gigantic ecosystem. This means that our design has to be A, backwards compatible, and it should be opt-in, so that existing programs can continue work. Let's start with a basic idea of how you may implement this in your language. So let's, for every object we have, add a small flag. And this flag basically just says, hey, is an object mutable? This is what every object in Python is by default. Or if the flag is set, it's immutable. Then we add an operation called freeze. And this operation basically just marks all objects and objects reachable from this object as immutable. So if we look at our two variables over there and we freeze x, then we can see how immutability propagates through the graph. This is beautiful. And lastly, there are some checks in the runtime that whenever you try to modify an object, throw an exception. So if we would try to assign something, the runtime would say, hey, you try to modify an immutable object, not cool. So with this basic idea and understanding in place, let's look at an actual Python program. So here we have a beautiful small script that, and I'm going to walk through it step by step. So the first import statement here creates a Python object that is mutable that represents this module. This import module does the same thing, but here critically we've also shown the pointer to the function object, which is a stateful mutable object in Python, because of course. So then we continue to this class, and this one creates another mutable stateful object that we somehow have to deal with in our design. And each method is also reified. We here don't visualize the init function, but there is this roll function which also has a pointer to the globals, and this is how you can access, for example, the random module. And now when we instantiate two things, for example, our D6 here, which is a beautiful die, this has a pointer to its type, and the same goes for our D12. Now, if we try to freeze our D6 here, interesting things happen. And this is that freezing propagates via the type and via functions through the entire system. So in this example where we want to preserve our beautiful D6, all of a sudden our D12 is frozen, and even worse, the entire interpreter crashed. Why is this? Well, it turns out that Python, at least the REPL, requires the sys module to be mutable because whenever you execute something in the REPL, it assigns to the underscore value in the sys module. This is not great. So this brings us to one of the generalizable concepts, and that is freezability. Basically, we needed a way to control if and how objects can become immutable. If we look at this program and roll it back a step, we can mark the sys module as unfreezable. So this sets a flag saying this cannot be turned immutable. And we can also go to the runtime and request this, and the runtime will say, don't freeze this. And any attempts to do this will result in an exception and the interpreter preventing you from doing that. All right, so the solution for the problem that the sys module has to be mutable is to make it unfreezable. Great, but this again brings us back to our core problem of every object is interconnected in Python. And this is where detachment comes into play. This is a way to control how far deep immutability propagates. So again, if we have our beautiful program here, and we wanted to free as our D6, we can do the freeze call, and it propagates to this type. But at the point where we encounter a function object, this immutable stateful object, we pause for, or we don't pause for a second. As part of the freeze, there is logic that detaches the function from the global scope, so this prevents it from propagating through the entire system. And we do a small static analysis that finds all global variables that we actually need. And this way, we've detached the function from the global scope. And now, once we've done this as part of freezing, freezing continues to propagate, and we have a frozen D6 object. This is perfect. So the solution for this interconnected web that we have to deal with is detachment. Though this story is not done yet. If you try to run the roll function, you get an exception. And the reality is that a lot of Python modules are stateful. The solution here is, again, detachment. I sadly don't have time to show you any details of this way, but I encourage you to read the paper where we discuss 5 different ways of detachment. Let's talk a little bit about the implementation. We've authored our implementation on an alpha version of Python 3.15, which was the most up-to-date version when we submitted the paper. Our changes are 7,000 lines of logic to do freeze propagation, detachment, and plus escape hatches. 7,000 lines in a context of a code base that's 2.7 million lines of code is good. And we provide this, of course, as a workable and reusable artifact. As part of our implementation, we've also support atomic reference counting for immutable objects. So this is why we, for example, needed to implement that in the core of the runtime. And there's a question, how do we enforce this? And the simple answer is we use a write barrier. Let's visualize it for a second. Let's say we have this function, this beautiful function that increments a counter. The current version may look something like this, but to support immutability, you have to add a small check. And this PyCheckWrite basically just says, hey, if this object is mutable, you may proceed. Otherwise, we have to emit an error and propagate this error upwards. In total, we needed to insert this write barrier at 148 places in the runtime. But with this, we covered the entire interpreter, all standard libraries, and so on. Evaluation. We have, to evaluate backwards compatibility, we've ran the entire CPython test suite. For reference, this is about 600,000 lines of Python code that works. And we believe that this shows that our design is opt-in and backwards compatible. Of course, there's also a question about correctness. And for this, we've added our own tests, about 3.6 thousand lines of code, testing various bits, and whenever we found something, we added it. Let's talk about performance, which may be super interesting, and some people have been waiting for this. And for this, we've used the PyPerformance benchmark suite. This is a typical benchmarking suite used in Python. And this is the graph produced by it. Of the significant results, we got a slowdown of 3.6%. In the graph, I will mark it right there. And this is of single-threaded programs, so none of these use immutability. We consider these results very good, given that we haven't spent time on optimizing it yet. We've added write barriers and hot path of the runtime. And other proposals like free-threaded Python target a slowdown of 10 to 15% of single-threaded programs. So having a slowdown of just 3.6% geomean is quite good. But let's talk about the thing why we've actually been doing this, right? And this is to share objects across sub-interpreters. First, we've benchmarked how long it takes to freeze an object opposed to copying it once, right? And as you can see, freezing is in all cases faster. In some cases, that includes custom classes, like the student, as actually significant, like larger by a big portion. And this is also visible if we distribute work across sub-interpreters. So in this benchmark, we've scheduled 4x4 matrix inversions across several sub-interpreters. And the blue graph at the bottom shows what is currently possible on stable Python. So this is for every cent, you have to create a copy of it, while freeze is done once. So we freeze a matrix once, and afterwards we can freely send it to every sub-interpreter to do the matrix inversion. And that is one of the big reasons why we see such a performance increase. Yes, in the paper you will find a lot more details about this and external things. So there is a discussion about design goals and how we fulfill them, an explanation of how freeze propagation works. As part of this, we also needed to handle freeze failure. So how do we undo this and surface it to the user? We also needed to implement a way to collect immutable garbage without tracing. As I mentioned, there are 5 different types of detachment which we've documented, plus escape hatches that the community has asked for. And there's also pre-freeze hook, among other things. This slide is limited, like the slide space. What are the next steps? Well, we've already created a Python enhanced proposal to engage with the community, see if we can get this into language and get that accepted. Next month, we will speak at EuroPython, actually present our design and the benefits of this design. And as part of it, we will also talk to the core Python community, the developers of the runtime, to see how we can potentially shape the future of Python and enable safe concurrency in this language. Thank you very much.
Questions?
Hi, thanks for the great talk. So the mechanism you've introduced is really elegant, and it's like, you know, backwards compatible because users have to opt into it. But have you thought about how you can encourage users to add these freeze calls? Because it's no use if nobody wants to use it. Obviously, they're motivated by performance, but I'm just wondering if there's any way to surface that to like users to adopt this.
So a thing I haven't talked about, which may slightly already answer that question, is that some objects, as I mentioned, are already immutable in Python. So we provide a way to say this object is already logically immutable. You can actually, it turns immutable if you observe this. So integers, for example, or strings can already be shared without you needing an explicit freeze. And we see this as a like opt-in mechanism specifically when people want to share or want this ability to reason about it. So yeah, encouragement is based on what the users need and want, right?
Cool, thank you.
You're welcome.
Time for another question? Oh.
Hi, thanks again for the talk. Can you talk a little bit more about how the detachment works? Especially, is detachment more of like a device that we put in, or that it has any sort of operational aspect to it? Like, does that involve deep copying of all the reachable objects into the system library?
So when we started working on this, we found that we needed to detach 1 or 2 things, and it just became more until we like reached 5. And we figured out that there's actually a core mechanic of when before you freeze an object, would it be a custom type, you want to call a little bit of code. So you can, for your own type, define how it works. In most cases here, we've pointers and, like we've shown there, replace the global dictionary with a new dictionary and only copy over the references of the needed objects. But you could fully imagine a world where you do deep copies of everything. And you could define them for your own type if you wanted to.
I see. So just to clarify, these are objects that are inherently immutable, but through the awfulness of Python interpreters that they ended up being part of the mutable object.
They are inherently mutable. You can, every function, like function objects, you can just add new globals to it, new locals. There is not really a restriction. It's just that most Python programmers don't do that because it makes it really hard to understand what's going on. But functions are just stateful, mutable objects. There's nothing stopping you.
Got it. Thank you.
Is there one other question?
Hi, very cool talk. One curiosity question just about something you mentioned briefly is that for every object you added a very small flag indicating whether it was mutable or not. Have you done any profiling of how that affects memory usage?
So luckily, Python objects already have few bits that are not used in the header, and they specifically have a flags field. So we've added it just to this one, and the object header actually did not increase. But that is a very good question. Thank you for asking it.
Thanks again.
Thank you.
The third talk on the session is about Flux Heap. It'll be given by Jakavos Kolokasas.
Hello everyone. I'm going to present you Flex Heap, a dynamic I/O-aware heap resizing for managed application. Today, modern JVM systems such as Elasticsearch, Cassandra, Spark process large datasets from storage. So they require both large heaps and large I/O cache. On the one hand, large heaps reduces GC frequency. As you see in the table, from the execution of Wikipedia workload in Elasticsearch, where we have concurrent clients that perform document ingestion and query searches, in the case of a larger heap, the GC frequency is by 2 times lower compared of having larger I/O cache. On the other hand, larger I/O cache reduces I/O stalls. As you see in the table, the I/O traffic when we have larger I/O cache is by 4 times lower. As a result, partitioning available DRAM affects performance significantly. As you see, a larger heap increases the document ingestion throughput, but a larger I/O cache increases the query per second rate in search operations. So the challenge here is how much DRAM to provide for each use and how to do this dynamically to adapt to application different phases. One line of existing heap resizing mechanisms tries to reduce the GC cost to improve application performance. However, resizing only the heap for GC performance doesn't work. For example, in the previous experiments of Wikipedia workload in Elasticsearch, in this time frame, you can see we have both high GC and high I/O overhead as there are concurrent document ingestion and query searches operation. In this existing resizing policy, prioritize the heap growth to reduce the GC cost and do not consider the I/O. On the other hand, other work, they try to reduce the server memory usage by allowing more applications to run. However, when the heap pressure is high, they release little memory back to OS, and we have the same effect as with the previous resizing policy. Thus, none of the existing resizing mechanism considers the I/O cost. Today, users, to overcome this problem, they statically partition DRAM. They cap the maximum heap size, and the rest memory is used for the I/O cache. For example, Elasticsearch and Cassandra recommend to use 50% of the DRAM budget for the heap and the rest 50% for the I/O cache. However, static DRAM partitioning has 2 main problems. It's not straightforward to find the proper split and cannot adapt to dynamic application behavior. So in this work, we propose Flex Heap, a heap resizing mechanism that considers both GC and I/O cost. It dynamically resizes the heap, so the rest memory is used by the I/O cache. And Flex Heap is a resizing mechanism for G1 GC, which is the default OpenJDK garbage collector. G1 consists of 3 different collection types: young GCs, mixed GCs, full GCs, and concurrent mark cycles, where it scans the whole heap without stopping the applications to find live objects. After each GC type, we have Flex Heap that makes 2 main decisions: whether to grow or shrink the heap, and by what amount it's going to do it. Now I'm going to present you the design of Flex Heap, discussing how it decides to grow or shrink the heap, how it estimates the impact of GC and the I/O stalls, and how it decides the amount of the resizing step. Flex Heap decides to grow or shrink the heap based on the impact of the GC and I/O stalls on application performance. For this purpose, Flex Heap models the impact as a total loss potential cycles, and also in the paper you'll find a discussion for other alternatives. Flex Heap divides execution in intervals based on GC phases, and in each interval decide to resize the heap based on loss potential. So Flex Heap, after each resizing operation, waits to see the effects, so to avoid premature actions. If we see that the total cost decreases, then Flex Heap continues in the same direction, applying the same action. Otherwise, if the total cost increases, then Flex Heap identifies which is the dominant cost. FlexHeap compares the relative differences between each cost between intervals to see which cost has been increased more. Then it performs the appropriate action. So now how we estimate the overhead of the GC. GC in the G1 can be stop the world, which means that during the GC the mutator threads are stopped and they cannot run. And also we have concurrent GC phases, which means that concurrent GC thread runs alongside with mutator threads. So FlexHeap model this cost and convert it into loss potential compute cycles for mutator threads. Let's see for the stop the world GC. We interpret the stop the world GC like young GC, mixed GC, or full GCs in G1 as a loss potential from the mutators work during this pause, because all the cores are occupied by the GC threads. So we estimate this using the pause time multiplied by the minimum number of active mutator threads and CPU cores. For the concurrent GC cost is different. We count it as a cost if concurrent GC threads runs while mutator threads are waiting. For example, in this experiment, we have 4 mutator threads and 2 concurrent GC threads, and we have only 4 cores. So 2 of the mutator threads are waiting, and we count this as a cost. Otherwise, if we have enough cores to run both mutators and GC thread, then we ignore this cost. Then the I/O cost now is different from GC cost for the estimation. The GC consumes CPU cores that mutators could use. In the case of the I/O, it blocks mutator threads waiting from storage to take the data, even when CPUs are busy, so creating queuing effect, which affects application latency. For example, if you see in the figure, we have, in this phase, we have one thread that's waiting for I/O, but the whole CPUs are occupied by the rest threads. Then we have 3 CPUs that are, one CPU that is idle, and because the other threads are doing I/O, and then again, all the CPUs are occupied. So we count the I/O cost as the sum of the stalled mutator CPU time. Today, Linux kernel interface do not expose per mutator I/O stall time. The I/O weight is per process level and not thread level. And also, more fundamentally, is that kernel cannot separate the I/O stall time from the scheduler delay time. So FlexHeap approximate permutator I/O stall time using eBPF on sketch switch, and we track mutator time blocked in this state, which represents that it's waiting for I/O. After FlexHeap deciding the proper action that will perform, it needs to estimate now the resizing step. The goal to FlexHeap is to shrink the heap without hurting G1 post-time goal. G1 estimates the hidden target size required to satisfy the post-time goal. And FlexHeap ensures that the shrinking step will leave enough space for the required hidden space. So we have the DRAM budget, we have the DRAM that is backed by the heap, and the rest is uncommitted. Some of this backed DRAM which is occupied by the heap is used, the rest is free. So we see how much is the hidden target, and we account for the shrinkable budget. Now, based on this shrinkable budget, we use a sigmoid function to choose how much of this budget we are going to release, and we do proportional step based on the estimated cost change. Now let's move on to the evaluation. We implement FlexHeap in OpenJDK 21, and we identify workloads that exhibit continuously changing heap I/O behavior. We run Spark with Spark SQL using TPCDS workloads, Elasticsearch using ESRally. We use 2 main baselines, the G1 that resizes the heap to reduce the GC cost, and we use the latest version of the resizing mechanism of G1 from OpenJDK 26. And we use also VG1, which resizes the heap to reduce the memory usage. We use a server with 2 TB NVMe SSD, 256 GB DRAM, 32 cores, and we limit DRAM capacity with zip groups. In here, we show the potential of flex heap that improves Elasticsearch throughput. We have the normalized throughput based on the G1 resizing policy, which we use the guidelines of Elasticsearch that says use 50% of the DRAM budget for the heap and the rest for the I/O cache. We use the VG1 and we show the flex heap with the third column. And we use two different DRAM budgets for Wikipedia, Cohere Vector, Dense Vector, and OpenAI Vector. FlexHeap improves throughput between 5 to 20% compared to G150, the ingestion throughput, and by up to 30% compared to VG1. And also FlexHeap improves the search throughput by up to 7 times compared to G150, and by up to 5 times compared to VG1. Also, we investigate how FlexHeap improves Elasticsearch latency. For the ingestion task, FlexHeap improves P99 by up to 10% compared to G150 and by up to 30% compared to VG1. And for search task, FlexHeap improves P99 by up to 25% compared to G150 and by up to 2 times compared to VG1. Here is how FlexHeap adapts to Wikipedia workloads behavior. If you see is the first run with the G1 using 90% of the DRAM budget for the heap and the 10% for I/O cache, G150, which used 50% of the heap for the 50% of the DRAM budget for the heap and the rest for the I/O cache, VG1 and FlexHeap. If you see, FlexHeap in these phases adapts better to application behavior compared to the rest resizing policy, and this is shown by the reduction by to 17% in the average I/O wait time. Next, we show how FlexHeap improves Spark SQL's performance, and we have FlexHeap versus G1 using 16 and 32 gigabyte DRAM, and versus vertical G1. In the y-axis, we show the execution time reduction percentage, and in the x-axis, we show the cumulative query fraction. We see that 43.7% and 27.2% of queries have execution time reduction more than 10% compared to G1, and compared to VG1, 30%, 26% of queries have execution time reduction more than 10%. To conclude, JVM-based search and analytics systems need more memory for both heap and I/O purposes. Partitioning memory to reduce both GC and I/O cost is a challenging problem, and existing heap resizing mechanisms do not consider I/O cost. FlexHeap partitions DRAM by estimating the loss potential from GC and the I/O stalls, and takes two decisions dynamically at GC phase boundaries: grow or shrink the heap, and by which amount. And we see that FlexHeap improves throughput by up to 33% and up to 50% compared to G1 and VG1. Thank you for your attention. I would like to answer your questions.
Questions?
Oh yeah, thank you for the great talk. I wonder if your methodology, your approach can be extended to other garbage collector like JetGC or Shenandoah, because I think large scale server may use different garbage collection than G1. Yeah.
Yeah. Thank you for your question. We also think about this. Sure, we need to see there the cost of the GC. I mean, because all these are fully concurrent. We have to see how we estimate the GC cost. Maybe this methodology about the estimation, it's okay. The next thing is, whenever we're going to take decisions in these garbage collectors, which are fully concurrent, we need to see where they have stop the world phases, if they have, in order to take the decisions. So yes, it will need a bit rethinking if you're going in a different collector.
Oh yeah, thank you.
Yes.
Time for more questions. No pressure, some pressure.
So this heuristic that you mentioned which was based on essentially platform threads and what platform threads that can run to make decisions whether or not to adapt. Have you thought about virtual threads and how that's going to affect this?
Yes, no, we didn't see it with the virtual thread. It's a next step, I mean, to see how this can be used for virtual threads. Yes. Thank you for the mention.
Still have time for more questions? I have a question. Do you have a sense for how close to optimal your technique does, or is there any way to measure that, like what the optimal decisions would be in hindsight?
Well, the optimal decision, yes, well, because this finding the optimal using a model, it's not very easy because in different infrastructure that you run, you might change. You don't know the device, you don't know the CPU cores that you have. So having a model that you can use predefined weights for the GC and the I/O, it's not so easy. So we use the sum of this cost in order to know that, in order to not use weights. Now for the optimal, to find the optimal, it's not very obvious which is the optimal in each runs and how you are going to find it. Yeah.
We still have time? One thing, this is more of a clarification question, but I didn't fully understand how, like, the number of mutator threads is relevant. Are you adjusting the number of mutator threads, or how does that go?
Well, the number of mutator threads can be increased, decreased during execution based on the application, because it might create some threads, then stop these threads and create some others. Because we are inside the runtime, we know when the application creates a new thread, and we count it and we use it to monitor it in the eBPF.
Nice. Last chance. All right, thanks.
Thank you very much.
The last talk of the session and the conference will be given by Kong Ma, and it's about virtualizing continuations.
Can everyone hear me? Cool. Hey everyone, my name is Kong from University of Waterloo. Thank you everyone for staying up to the last talk, and I hope everyone have a good time here. I personally have been camping in the mountains for the good part of this week. I certainly have fun here. Okay, so this talk is about virtualizing continuations, and you need to understand what effect handlers and multi-shell continuations are to understand this talk. And I will introduce these concepts after I give you the big picture of this work. So effect handlers and multi-shell continuations are powerful language features, and they are compiled using distinctive techniques. Effect handler is compiled usually using stack switching, and the multi-shell continuations is compiled using stack copying. And these two techniques are in conflict with each other. And in this work, we introduce a novel technique called virtual continuation to resolve this conflict. Now, coming back to the background. Let me introduce the concept using the example of n queens. N queens is a problem that asks you to place n queens on a board of size n times n, so that no two queens are on the same row, same column, or same diagonal lines. And this is a typical implementation of n queens. You have a function safe that check whether a placement on a row is compatible with a partial solution. You have a recursive function place, taking in the size of the board, the row that you're currently trying to place the queen on,
and the partial solution. And inside the place, you have a for loop that iteratively tries different placement on that row. And for each try, you check whether it's safe or not. If it's not safe, you continue to the next loop. And if it's safe, you recursively call place to try on the next row. This is the same function, just have this variable name shortened for the sake of space. And I'm going to show you a second flavor of the implementation. In this implementation, I use effect handlers. And let's look at the difference between these two versions. Instead of having an explicit for loop, I perform a choose effect given a list of choices. And instead of, say, continue when an option is not safe, I perform a fail effect. So in a sense, this version abstracts away search strategy. And where is search strategy specified? Well, they're specified in a handler somewhere up the call chain. And in this example, nQueens is a function that installs a handler inside the body. And inside the handle with expression, we see an invocation of place. Now, when the callee performs a choose effect, the control will be transferred to the handler here. And we can see the familiar for loop inside the handler. Raising an effect and transfer the control to handler is not so much different than calling a function and having the control transferred to the callee. The magic of effect handler comes from this extra parameter k, which every handler takes in. K is the continuation from the place that raised effect to the place where the handler is installed. In a program, the K can be resumed at any time. And when that happens, control will come back to the place where effect was raised, carrying choice as an argument. Effect handler gives you a way to do this kind of non-local control transfers back and forth. And it is a very powerful language feature. It allows you to write very modular code for some algorithms, particularly the one involves search and backtracking. In this example, we see that the continuation is used inside the loop, and it's used multiple times. This is called multi-shot continuation. It is challenging and to implement multi-shot continuation efficiently and correctly. Now, let me give you a short digression to the semantics of effect handlers. Traditionally, effect handlers are dynamically scoped. Think of exception in Java. When an exception is raised, the closest enclosing handler at the runtime is used. I come from a camp where we advocate for lexically scoped handlers. The semantic says that when control enters a handler's scope, a handler capability is generated. It is passed down the stack and used at the raise side. This semantics is commonly found in resource languages such as effect and Laxa, and I heard that Oxcaml is experimenting with this semantics too. So to give you a flavor of lexical handlers, let me show you how the program will look like with lexical handlers. For nQueens, we need to parameterize or add a binder for a capability variable to every handle with expression. And we need to pass this capability variable to any place that could raise effect. Furthermore, we also need to parameterize every function that could raise effect with an extra capability parameter. And every perform expression now needs to take in a capability as well. Effect handlers are a unifying control flow mechanism. They introduce first-class continuation into a language, and continuation can be single-shot or multi-shot. Multi-shot continuations are very expressive, as we've seen from the earlier example. Now, effect handlers, as I said before, is compiled using stack switching, and multi-shot continuations are compiled using stack copying, and these are in conflict, and I'll show you where they are in conflict. I'm going to show you how these two techniques work. Here, again, it's the same function, nQueens and place. The orange stack represents the activation frame for nQueens, and the green stack represents activation frames for place. When we install a handler, the runtime allocates a new stack and start the computation on that new stack. The runtime also takes the address at the bottom of the stack, represented by this pink triangle, and use that to serve as the reference or capability for the handler, and pass that reference down to the call chain. So now the execution is at a place where we're about to raise the choose effect. What happens is that we follow the pink pointer to the place where handler is installed, And we simply switch stack pointer to the place where handler is installed, like this. And now control comes to the handler in a place where we are about to resume the continuation. Similarly, we simply switch the stack pointer to the green stack. And that's where the name comes from. We model the capturing and resuming of continuation by switching the stacks. Something that I did not mention in the prior slides is that this use of continuation is actually in a multi-shot fashion. And to be able to resume a continuation in a multi-shot, we need to copy the stack, because otherwise the stack could be destructively modified. And that's what we'll do here. When we resume continuation, we first copy the green stack, and then we switch the stack pointer to the copy. And you might already notice a problem here. By copying the stack, we're also copying the reference to a stale pointer to the handler. And the semantics really says that this pointer should be pointing to the copy of the handler in the green stack. So here's the challenge. The stack switching technique refers to handlers using stack addresses, which is incompatible with stack copying. To solve this problem, we borrowed the idea of virtual memory management. In a virtual memory system, all processes have an illusion that they own the entire memory space. And whenever an address is used, it goes through the translation of MMU and eventually goes to the physical memory. And if you squint your eyes hard enough, you can see a similarity between processes and continuations. Whenever a stack pointer is used in a continuation, we really wish to have an indirection mechanism that point this pointer to the right copy or the local memory region in a continuation. And that's what we did. We implement a runtime library called SMMU that carries out this redirection. To note that we still have the virtual memory provided by the operating system, but because it's transparent to our design, I'm not going to talk about it in the rest of the slides. Now let's look at how virtual continuation works. The key idea is that we partition the entire memory space into zones. And every address now is a virtual address. The top portion of an address is what we call zone number. Middle portion we call handler ID, and the lower portion are stack offset. As you can see from the diagram here, we have two stacks. They all live in zone 0, so they have the same zone number. And because there are different stacks, they have different handler ID. Now, when we copy a stack, this is important, we bump the zone number and copy it into a higher zone. And crucially, we copy it into the same relative offset inside the zone. This ensures that the same copy of the stack will have the same handler ID in their addresses. Now, after we lay out the memory this way, let's see how an address translation works. Say that right now, we're raising to a handler installed at 010. The runtime takes over the control, and it looks at the current stack pointer and determines that we're currently in zone 1. Runtime simply updates the virtual memory by replacing the zone number to the current zone. And we get the address 110, which is exactly the right copy that we need. In our system, a stack pointer's upper part is meaningless. It is contextualized at runtime according to the current execution point. Now, we've only covered a simple case in this example. In general, the target handler can be in a different zone. I'm going to show you a more complicated example. We have a yellow stack, a green stack, and a blue stack. And the blue stack captures an address from the green stack. Now let's copy the blue stack and raise to the address 010. This time, if we naively update the zone number to the current zone, we get address 110, which doesn't exist. Instead, for each translation, the runtime performs a zone walk. We first look at the virtual address and grab the target handler ID 1. And we look at the stack pointer, grab the initial zone, and the runtime remember these two values. And then we start a zone walk. At every zone, we ask a question. Is there a handler with ID 1 in this zone? And how can we check? Well, it's a difficult question because at that address, you could have data or you could have garbage. We perform a clever trick. We look at the first handler in the zone. We grab its handler ID and compare it with our target handler ID. Because our target handler ID is smaller, we know that the target handler is not in the zone. But why? Our runtime maintains two important invariants for this presence check to work. First, handler IDs are assigned monotonically. For example, in these three nested handlers, when they're reduced at runtime, they will be given handler ID in increasing order, like 0, 1, 2. Second, handler capabilities are scoped lexically, which is dictated by our lexical handler semantics. Now, installing a handler corresponds to the start of the lifetime of a continuation. Due to lexical scoping, this continuation can only reach to handlers that have already been allocated with smaller IDs. And handlers within this continuation are allocated later with greater IDs. Therefore, every handler demarcates the inside and outside continuations, with inside continuation having greater IDs and outside continuation having smaller IDs. Now, coming back to the illustration. When we compare the edge of the zone, which corresponds to the boundary of continuation, we are sure that if the target handler is smaller than the first handler in the zone, the handler doesn't exist. Therefore, we continue the zone walk. Now we reach zone 0, and we look at the first handler, which has handler ID 1, comparing with, 0, and comparing with 1, we find that our target handler is greater. So we're sure that the handler is within zone 0. And the reason we prove the correctness of it in the paper. So coming back to our virtual address, right? We know that our target handler is in zone 0, so we remove the zone number and replace it with the correct zone number. And that gets us to the correct handler. Let's talk about performance. Zone walker carries out one comparison at each zone. The zone depth is a constant in most common programs. Therefore, each zone walk incurs a cost of a small constant. About the correctness of zone walk, well, it relies on two important invariants. The runtime allocates stacks with monotonically increasing ID, and the lexical scoping of handlers and handler capabilities preserve the monotonicity, and thanks to this monotonicity, a single comparison determines the presence of a handler. We formalize the language and prove that the language with zone walk will find the correct handler, and we prove this with a simulation argument. As for evaluation, we implement a virtual continuation in Lexa runtime, a language that we own, and we call it multi-Lexa. We compare its performance with the base Lexa, which was published in WUPSA 24. Base Lexa also implement stack switching and stack copying, but due to the lack of virtual continuation, it can only support a limited form of multi-shot continuations. The first question we ask is that, how much overhead does the additional bookkeeping in multi-Lexa introduce? We collect a suite of benchmarks, and we run them on both base Lexa and multi-Lexa. And you can see that overhead is sometimes positive and sometimes negative. That is because base Lexa also maintains some bookkeeping and allocation. So depending on the nature of the benchmark, the overhead is exercised either in base Lexa or multi-Lexa. But the takeaway from this experiment is that the overhead of zoning and the zone walk is not that significant. The second question we ask, does multi-Lexa unlock significant speed up by enabling the parallel execution of multi-shot resumptions, which is not supported in any languages so far that support lexical handlers? We collect a suite of algorithms that can be easily parallelizable, and as we can see that as we increase number of threads, we do see a noticeable speed up. The different trends we are seeing here is due to the way how algorithm is implemented, not due to the language runtime. In conclusion, I've shown you the technique of stack switching and stack copying that are used to implement effect handlers and multi-shot continuations. And I show you why they're in conflict. In this talk, I introduced a novel technique called virtual continuation that makes these two techniques compatible and bring forward the full expressivity of effect handlers to the world. Thank you.
Questions? You said something about the MMU and physical memory, and it was a part you blurred out. I don't know if that's interesting to talk about.
A little bit. So in the implementation, we actually utilize the fact that we own the entire virtual memory space, which is huge, that allows us to do the zonings. Okay. Mm-hmm.
You were saying that the lexical scoping of the effect handlers meant that your walking was sound. Do you avoid mutation or leaking the effect handlers so that they can't, because they could escape their lexical scope in that way?
Good question. So there are works already done that address this problem. Basically, the capabilities, the type system ensures that capability don't escape their scope.
Other questions? So it seemed like this builds on your prior work and solves a problem in your prior work. Could you say more about the context of your overall work? Like what's next, either following on the improvements you made here, or what other improvements would you want to make to your overall body of work?
Right. So this work starts from the implementation of lexical effect handlers. We compile a high-level language with a lexical effect handler to assembly, right? And then we find that we can support multi-shell continuation because of the problem I introduced here. And this paper brings back the full expressivity to the language.
So for this effect handlers, I guess you right now implement it in a specific language.
Mm-hmm.
Like say I want to do a similar thing in Haskell to have multi-shell continuations. Would I need to have compiler support for this, or would there be some way to implement this only in the Haskell runtime, or in the level as is, in language as is?
Well, good question. I'm not too familiar with Haskell ecosystem.
Any language, I guess,
yeah.
Not necessarily Haskell.
Well, I guess if you have the control of the compiler and the runtime, you can do that. For example, our work on Uppsala 24, how we use the stack address to represent the reference to the handlers are adopted by OxCaml. So I guess if you own the entire compiler pipeline, you can do something like this.
Okay. Yeah. Thank you.
Mm-hmm.
You said it was adopted by what? I didn't hear.
OxCaml.
Oh, okay.
Yeah, but they're still in experimenting mode, so I can speak for them.
Time for another question, if there is one. Oh.
Kind of a follow-up question. Do you think your approach can be implemented on top of WebAssembly, which only has stack switching?
Yeah, let's see. I mean, our implementation basically assume you have the control of a big memory space, right? I know WebAssembly have linear memory space, which might be tricky to do such things. However, our implementation is just one way of implementing the idea. Our formalism actually support many different ways of doing things. For example, we could implement virtual continuation using a nested list, right? We have a list denoting zones, and inside each element we have different lists denoting handler IDs. If you do indirections through that way, I guess it might be, have a fewer requirement for your runtime.
Thanks.
Thank you.
Thank you.